So, well, good morning, everyone. Thank you all for being here. And I just want to start by giving a special thanks to everyone that was organizing this workshop, because it would have been a big pain for both of us if it wasn't for all of your help. So I want to also start, since it's early, to start getting some energy. So let's give a round of applause for all of you. Now, I also want to thank our speakers. We still are missing one that because he just landed. Our speakers today, they are very busy, and today we are lucky to have here Professor Jorge Vieira, which is our new coordinator, and he's in a conference right now. Then we have Professor Elidio Lopes, which he literally just landed in Lisbon and he's finding a place that, so he can speak to us. And we are lucky that Professor Luis Mel is not on the OCDE meeting today, and we have him here in Lisbon. Uh, so, uh, today, this morning, actually on the train, I realized that our three speakers are our three coordinators that we have uh, throughout our 5 years of, well, bachelor's and master's. So, yeah, I think I was going to start in order, but since Professor Elidio is not here yet, we will start on the other order. So I don't know if Professor George, do you want to start?
Okay, yes, I can start.
Thank
So shall I speak in English?
Yes, please.
Okay. Okay, so good morning, everyone. So first, I would like to actually thank your invitation to uh, to tell you this brief message as a new coordinator for the Left and MEFT. I would also like to thank Professor Luis Melo for the precious help that he has been giving us in this transition, and also you, particularly to you for your excellent work so far. So I'd like to also to share with you that Professor Guilherme Liano will be the vice coordinator. Unfortunately, he cannot be present today because of a schedule conflict. He is also giving a presentation as we speak. As Bruno said, I'm in a meeting outside of the country. I cannot be there, unfortunately. I would really like to be there in person with you, but this was not simply what was not possible. So let me just give you a few words about myself. So my name is Jorge Vieira. I'm a professor at the physics department. I'm a member of the group for lasers and plasmas. I work in theory and simulations, and I'm interested about the interaction between intense beams of particles and lasers with plasmas and their applications to compact accelerators, light sources, and so on. So now me and Professor Guilherme Lian, we are very we want to give our best for our course. We also count on you, on your pressure collaboration. We treasure your ideas, your suggestions, your opinions. So please feel free to share them with us. Your contribution is fundamental for us to keep improving. Finally, I would like to wish you um, an excellent workshop. I hope that you enjoy this opportunity to share your work and you have some fun during this process. And even more importantly, I really hope that you just thoroughly enjoyed developing your project so far, and that you're proud and happy with your accomplishments until this point. So thank you and enjoy the workshop.
Okay, so Professor Luismel, would you like to continue? And maybe, Boss, could you give us back some light now? Thanks.
Let there be light. Okay. Good morning to everybody. Thanks for the invitation to participate in this opening of this workshop. This is already a long-standing tradition of math. So where there is a workshop, a scientific workshop, organized by you. So let me tell you, I never organized anything when I was in my last year. So it's just great that you organize everything. So from logistics to the technical part, everything. So this is just great. The other thing I would like to say is that, and it's something I think you're going to remember all your life. I would, if I were there. So the other thing I'd like to say is I'd like to thank you because I had this 2 year term as a coordinator. Being a coordinator is, well, let's say it's a bit tiresome. You get very, very tired. So George, yeah. So you're very lucky because George is not only is great, but he's much more organized than I am. So that is good. But um, it was great. So it was very tiresome, it was terrible, but I couldn't do almost anything else. But it was very good to be with you and do things with you and be close to your problems, to your issues, to what you want to do. And many of you know me better because were my students in my last year courses, and so that you know me a little bit better. Others know me from you know from being the coordinator. The thing I would like to say about you all is that you are all this is a very special. So Blank and Map are very special things. You are very very special people, and as life will go on, you understand that more and more. And for me, I was very happy to be able to be close to you and very honored to be close to you and trying to get your life, you know, a little bit better once in a while. Although most of the time was just running bureaucracy. But and so thank you very much. I think this is going to be a great workshop. I looked at the presentations, yes, of course, that is the agenda, but I looked at the presentations before, and so this is going to be a great workshop. And I know you were very busy doing the videos with Danielle. By the way, an applause. He's not here; he went away, but an applause to him because. And I would also like to thank Annabella and Martina because they are those of you who have talked to both many of them, you know any of the two, you know they're really really just great. And so thank you very much. Get on with it and let's do it.
Professor Elidie Lopes, welcome. I hope you had a nice flight. I'm just coming here so it doesn't look like I'm just facing the back from you. Are you here?
Um, yes, I'm here. Yes, I'm in literally in the airport in Lisbon. Yeah. Hello.
Hi. If you would like to give us some of your words, please go ahead.
Yeah.
Thank you.
Okay. Well, first of all, two things. That's close because I think it's the first time I have the opportunity to be with all the left and math students. I hope you are listening me well. Let me acknowledge Luis Melo for his work as coordinator. Is a great person. He has the communication skills with the students, second to none in the department. I was saying technical, and for that, Luis, thank you very much. I already told him personally, but in particular for you students, and of course, like we, like myself, we are still open to help you as teachers any way we can. Of course, also welcome Jorge Vieira, that also is the new coordinator, and also will have the same commitment and passion and resolve that all the previous coordinators have in the past. Now, about the workshop, uh, in the format is a series, I think the unique one has been created for me a few years ago. I'm a great passionate about the workshop because is let's say a training desk for a skill for the future. You know, most of you are very competent researchers and scientists, but are natural leaders. And this is a very nice place for you to start to organize and to be working group. And most important, because sometimes you believe, but other times you need to be led by others. And to have the balance, to be on this kind of situation is very important. And I will say is these kind of skills, if I take into account that your intelligence is not a problem, your ability to understand things is not a problem, where we can help is, among other things, is create the network and the connections and the way to work with each other and create basically sometimes here, as Luis was saying a moment ago, you have some of the tension, difficulties you can find in life. The workshop is one of these little situations that you can diffuse this and go forward. Now, yeah, basically is what we say. I hope you enjoy a lot the project. In my time, maker videos were not very popular, and meaning the coordinator need to be tough. And that's actually the reason you should do things that you don't like. At least you should find ways that things are important. I hope you have done the videos, and I hope you have great videos. And yes, basically, it's the most important message I want to have from me. Um, and be committed always in your projects. This is very important. And do your best for for being able to achieve not only what you do about your work. Last point, and go what I said. I see many students, and not only in Texas, but in Cambridge, Oxford, around the world, brilliant students. They academically finish their courses and degrees with amazing grades. But then you ask the question, why this person do not, I mean, you succeed in life, of course, but do not succeed with compared to others. And I think the reason comes along is because many times they are very competent, very intelligent, articulated, but do not have the communication skills, the capacity to work in group, the capacity to be creative, and so forth and so forward. And that's what this is important. This is one of these components that can help us to prepare you for the future, which means be a stage that you can actually use all your abilities to really promote yourself, your country, your institution or company where you work or whatever you are doing. This is very important. You should invest. I know it's not easy. You should take seriously. You have the rational thinking you do to do science. You should also think about these things. How you approach this. I'm doing the right thing. I have the right connection. What skill I can improve. And this can also be a platform for you to try to eventually have additional skills, courses, and so forth. Okay, well, uh, I have no idea the audience. If the shared person, I think is Bruno. I think I will stop here. Just acknowledge all of you and all the participants, and have a wonderful workshop that I'm quite sure it will be. Thank you, Bruno. Hello.
Thank you, Professor. We were just clapping, and I don't know if you could hear us.
Wait,
But thank you.
no, not at all. Not at all.
I have to agree with you that being able to speak to an audience is very important in any field of science. Uh, we will be seeing you during the coffee break as well, correct?
I will pop in. Yes. I will. Okay.
Perfect.
Thank
Thank
you.
you very
Thank
much.
you, all of you.
See you
Thank you. Sorry for
at the
that.
coffee break.
Thank you. Cheers. See you. Bye bye. Cheers.
Bye.
Okay, so before we actually start with the workshop, I want to give some logistics notes. Okay, so as you know, we have two forms that we have to fill in for evaluation. We have one that you have to fill for each presentation that you see, all right? And then you have a second form, which is the evaluation of the functioning of the workshop, which you only fill out once at the end, all right? In regards to the evaluation form of everyone individually, you can fill it several times, but the only one that counts is the last one that you fill for each person. All right? And the other thing about logistics that's important for you to know is that we're streaming on YouTube. And so everything that you say here is going to be streamed on YouTube, and we have a very good microphone, so just keep that in mind. And so before we start, I just want to say that in the last couple of days, I've had the opportunity to reflect a bit on the path that we've started. And I think it's really great that maybe we can keep some of the energy that we had maybe in our first year when we were sending happy birthday, all 70 of us, to each other, or when we were helping each other on courses, etc., etc. And keep that spirit up and use this as an opportunity to be together. And without further ado, I think I'm going to pass the word to the chair. Thank you.
And by the way, the microphone comment is more specifically to the people near the microphone. Please don't be too pressured speaking over here. But yeah. Não tem microfone para eles. Não sei não.
So, hello everyone. We're going to have our first presentation now from Pedro Figueiredo on particle physics and candidate dark matter model. You can come to the stage, please. Is that not it?
Vídeo primeiro, né?
First, the video. Yes.
So maybe before we start, another important logistics note that was in the notes, which is we pass first the video, then the presentation. While your video is going, please go to the front of the microphone.
Hi, my name is Pedro Figueiredo and I'm an engineering physics master student at Instituto Superior Técnico under Professor João Paulo Silva and Professor Jorge Romão. Today we'll be talking about particle physics, dark matter and machine learning. The Standard Model is the gauge theory that describes all known particles in the universe and their interactions via the electromagnetic, strong and weak nuclear forces. It is a very successful theory since it makes predictions on how the fundamental particles behave, and almost all have been verified experimentally. One way of testing the theory is by colliding particles at high energies in the Large Hadron Collider at CERN, the largest and most complex machine ever built, used to discover the famous Higgs boson in 2012. The Standard Model contains the matter particles like the electron, the force carriers, and the single Higgs boson. The Higgs boson is very important since it is associated with the mechanism that gives particles their fundamental masses. However, there are still unsolved problems for which the Standard Model does not provide answers, such as dark matter. Dark matter is so important that it accounts for about 85% of all matter, while all that we see in the universe, such as stars and planets, is only comprised in the remaining 15%. The name dark matter was coined in the 30s by Swiss astrophysicist Fritz Zwicky, who estimated that the comet cluster had hundreds of times more mass than what was observable. Since then, more experimental evidence for dark matter has appeared, such as formation and evolution of galaxies, their motion within clusters, and the cosmic microwave background spectrum. As physicists, we must try to tackle such problems by making models which are compatible with experiment, extending the Standard Model with more features that provide answers to our open questions. In our work, we study a model with 3 different Higgses, such that they can be considered good dark matter particles. This model has 2 distinct dark sectors, where each of the new Higgs particles, besides the Standard Model Higgs, constitutes the dark matter particles. After a complete theoretical analysis of the model and comparison with experiments such as LZ, Hess and Fermilab, it is possible to conclude that with the balance of both dark matter particles, we can achieve the correct amount of dark matter observed in the universe. Although the model manages to provide a good candidate solution for the dark matter problem, the computational analysis of such models can prove to be very inefficient and time-consuming. To address this, we implemented a machine learning algorithm to help probe the perimeter space and explore new possibilities. The algorithm comprises an evolutionary strategy which evaluates the fitness of a given set of parameters by calculating how far away they are from a valid region. It then keeps only the best points from that generation, makes copies of those points, and repeats the process onto the next generation until it finds points that pass all of the constraints imposed to the model. The algorithm converges quickly to valid regions where there are many good points. Conversely, it tends to stick to the first valid region it finds and stay there. To solve this, a novelty reward was introduced, such that the algorithm recognizes when a given region is already very densely populated and drives off to explore new uncrowded areas. After some tests, the algorithm proved to work drastically better than the random searches. This is a powerful evolutionary strategy with emphasis on parameter space exploration that can be used for any model analysis and will be an invaluable tool for future work.
I'm trying to skip this slide. Okay, sorry.
No, but can I skip this slide?
You should.
I should be able to, right?
Yes, I don't think so. Okay.
No,
You just point this way.
Yeah. Okay. Hi, I'm Pedro Figueiredo, now in person, and I'm presenting my work on exploring the three Higgs level model with dark matter and machine learning. We're all aware of how successful the standard model is and how it predicts the Higgs field. However, we can consider a scenario with more of such doublet fields, since this provides candidate solutions for open questions in particle physics. So, dark matter is a very well-fundamented problem. Here I have a picture of the bullet cluster. We know it interacts gravitationally at least, but it can also interact weakly with the standard model. There is no particle in our theories that may account for it, so we need to postulate new particles and study the standard models. We do this by means of the Boltzmann equation, which tracks the number density of dark matter along the expanding universe. We say the dark matter decouples from the thermal bath once its interaction rate is lower than the Hubble constant, which is of course related with the expansion. And when this happens, the final yield of dark matter is inversely proportional to the increasing to the interaction cross-section times velocity. Our model is an inert 2+1 Higgs doublet model, meaning that there are two different inert Higgs doublets that will constitute two different dark matter particles. These are our model is symmetric under a Z2 cross Z2 prime symmetry, meaning that there are also two dark sectors which stabilize themselves and their balance makes it possible to make a complete analysis of our perimeter space. So we've studied this model and we managed to publish the results, namely new vacuum conditions that are necessary for a theoretical analysis of the model, a complete perimeter space analysis, and also we found that there can be an equal contribution of both dark matter candidates to our model. We also implemented a machine learning algorithm in the form of an evolutionary strategy to explore the perimeter space. This algorithm minimizes a loss function, which comprises all of the constraints in our model, and we introduced a density estimation to incentivize exploration. These are some of the results. We see that for a simple random scan, we get very few points that actually pass the constraints, in this case only one. If we impose an arbitrary condition of the alignment limit, we reduce the degrees of freedom and the situation improves. However, it is not comparable with the drastic improvement of our algorithm SMART, which completely fills the parameter space. And this, of course, is an invaluable tool for any future analysis of any model. Thank you. Questions?
Any from the crowd?
Bruno, yeah.
I have one. Maybe this is kind of basic, but why 3?
Why 3? Because I already did it 2. So,
Queres ir para que slide? Queres ir para que slide?
Doomville, inert 2+1.
Yeah.
Okay. So if I only have one Higgs doublet, the model is an inert doublet model. It's the IBM. It is very constrained. So, what's avançado? Oh yeah. So it is actually here, that model. It was the first thing I worked on. And this one has a neat feature that models such as so dark matter, scalar dark matter models don't have, which is it is possible to populate this middle mass region.
and this is only due to the balance between both candidates in different sectors. So this is what this model brings to the table, where all other models in this kind of framework are all excluded individual mass region. This is So is there anything else? Well, this is more or less in the same topic, since, but I can go into further detail. So in this case, in this region, we are near the resonance of the Higgs resonance, and so it is always possible to have good points here in all of these models. And of course, if you go to higher mass ranges, everything is possible. But let's keep our searches where our detectors and experiments can provide information. So this model is especially neat due to this feature, where the relic is mostly within our second component, and our second component is the heavier component. So the light element is very probed and almost excluded. But if almost all of the contribution is within the second component, we managed to populate this middle mass region, besides the higher masses and the weapons. Yeah.
Next time you'll be using evolutionary machine learning models.
Yeah, sure. So this method is called SMITE, the Covariant Matrix Adaptation Evolutionary Strategy. It works, as it says, with a very localized multivariate Gaussian. And since it is very localized, it has problems regarding exploration. So it converges very quickly to the minimum, which is what we want. But then it fully sticks to that minimum, like the simulation in the video. And so we need to add this novelty reward to make density estimation and force the minimum to shift to some other new region around our good minimum and probe the parameter space around that specific region. So all the simulations, I don't know if I told you, but all the simulations on the next slide are actually so they start with the same number of points. So it is much better with the algorithm. I really was surprised with the result. Thank you so much.
Não, calma. Esse está com. Calma. Tem de vídeo. Deixa eu passar cá.
The standard model.
Oops, calma. Sorry. Spoilers.
Well, using state-of-the-art algorithms. Oh. So I'm pleased to announce that the next speaker is Pedro. We'll be using state-of-the-art algorithms to do flavor tagging aligned with deep learning models.
The Standard Model is the most widely accepted theory in the field of particle physics. It includes all the observed elementary particles and describes the interactions between them. This includes the quarks and the leptons, responsible for making up all the matter we see, and the bosons, known as the force carriers, that are responsible for mediating the interactions. However, the Standard Model is not complete. It fails to explain the existence of gravity, dark matter, dark energy, and even the observed neutrino masses. For this reason, several experiments are being made around the world to both test the Standard Model and to try to find new physics beyond it. Collider experiments are some of the main drivers in this research. They use particle accelerators to accelerate particles to near light speed. These particles are then made to collide, and the results of their interaction are collected in detectors stationed near the collision point. The gathered data is then used to study the phenomena that resulted from the collision. Several kinds of particles can be collided in these experiments, but if the objective is to study the strong sector of the Standard Model, meaning the quarks, gluons, and their interactions, in conditions of extreme energy density and/or temperature, heavy ions are usually the best choice due to their large quark content. These collisions create a very energy-dense region near the collision point, where quarks and gluons behave as nearly free particles. This state of matter is called quark-gluon plasma, or QGP for short. QGP is extremely short-lived, rapidly expanding and cooling down, which leads to recombination of quarks and gluons into mesons and baryons, in a process known as hadronization. This means that the QGP itself will never reach the detector, thus making it very difficult to study. There exists, however, a QCD object called the jet, created at the same time as the QGP and resulting from the decay of a quark or a gluon whose products reach the detector. If we can compare a jet produced during a proton-proton collision to one produced in a heavy ion collision, we will be able to see how the QGP affected the second jet, thus learning about the QGP itself. The difficulty now becomes the identification of the jet, or in other words, finding out which particle was at its origin. This process is called flavor tagging, and focuses on the inherent properties of each kind of jet to differentiate between them. B and C jets, for example, both present a displaced secondary vertex due to the long lifetime of the B and the C hadrons, respectively. During my thesis project, I will be working with one of the Atlas collaboration's most recent flavor tagging algorithms, called GN2. GN2 is a machine learning model characterized by having a graph neural network, or GNN, in its architecture, where each of the graph's nodes represents a track left by a charged particle in the detector. Another characteristic of the model are the auxiliary tasks of track origin prediction and vertex prediction, which have shown to better the results of the main task of jet flavor prediction. GN2 has been tested for proton-proton collisions showing good results, and this project aims to assert if its predictive power remains when accounting for the added complexity of heavy ion collisions. Thank you for watching.
Start. Ok, já está funcionando.
Hello everyone, I'm Felix. In this part of the presentation, I'll focus a bit more on the part of the graph neural network and on explaining the model that I have mentioned in the video. So, starting with graphs, why do we use graphs to represent these problems? First, they allow for the representation of data with variable size, which is very useful to represent a lot of different physical objects. In this example, we have a collision happening in a detector where three jets were created. On the left side, we can see one graph representation of this problem where each of the graphs nodes represents a jet. And on the right side, we can represent the same problem using three different graphs where each of the nodes represents one of the tracks left by the charged particles. And what does the graphical network do now? It basically finds new representations for our graph that will help our model better its prediction power. Going into the model now, it has a relatively straightforward workflow. We start by creating our inputs that have jet-related variables and track-related variables. Those inputs will go into the track initializer where an initial track representation is created. From this initial track representation, we will make an initial graph representation of our problem, and then that will be put into our graph neural network, which I will explain in a little bit. From that, we'll get a final jet representation that is used for the three tasks that were mentioned in the video, and I'll talk about them a little bit more about them. Okay, so for the graph neural network, as I mentioned before, the objective is to find new representations for our graphs. In order to do this, we have to find a new representation for each of the graphs nodes. If we are trying to find a new representation for, let's say, source node I, we'll first create a linear projection of itself and its neighbors, that in this case are all the other nodes, and use it to calculate an edge score. An additional linear projection is made for the source node that is used the edge score to find its new representation. This is made for all the nodes, and then we'll have a new graph representation that is put into the graph neural network again at least 2 more times. The auxiliary tasks I mentioned, we have 3 tasks in total: the main task of jet flavor prediction, and then we have 2 tasks of track origin prediction and vertex prediction. These 2 tasks have shown to help the model reach better performances, they are using the loss function that it uses to optimize its iterations in training. To conclude, I just wanted to talk a bit how much the performance of GM2 was enhanced comparing it to the its predecessors. So in case of GM1, we see it's almost at 2 times better. If we compare it to the L1 series that did not yet have a graph neural network present, we can see that its effects are very reasonable. Thank you for watching, and are there any questions? Jets. Okay, so the jet. Okay, so when the collision happens, we'll have a lot of energy. We'll have very heavy quarks and very energetic gluons. They will start decaying into, well, as it shows here, in a lot of different processes. We'll get gluons that will decay to more gluons possibly. Quarks can just radiate a gluon that itself will decay, and we'll have this shower of particles that is created very near the collision point, and it will, in the case of heavy ion collisions, transverse the QGP, travel through the QGP, and will be affected by it. So if we can compare it to a jet that didn't have to go through the QGP, we can see some of the QGP effects does stay. Yeah.
So you said that these heavy ion collisions brought more complexity to your problem. Can you expand further on that?
So usually, the most common collided particle are protons. In case of heavy ion collisions, we'll see here that their size being relatively big is very important. There's a parameter called collision centrality that basically measures how far apart the centers of the colliding particles are, and in this case, the higher collision centrality, the lesser this distance will be. And since we have a lot of protons and neutrons there, the more binary collisions we'll have, which will first of all increase the energy density in the region, and we'll always have our detector lighting up all around, which isn't necessarily the case for proton-proton collisions. And we'll also have a lot more of something called the underlying events. It's basically all the events that happen that we aren't necessarily studying. And the model will have to deal with them and ignore them, let's say, try to differentiate them. Thank you again.
Não mencionava? Exato. We'll be right back. No, we'll be right back. Exato. Print.
The next in line is Inês Freitas. She's gonna talk about her work on wearable sensors to monitor the physical condition of firefighters in real time.
As climate change intensifies, the frequency and severity of wildfires continue to grow, posing greater risks to both the environment and countless lives. In Portugal alone, the average annual area affected by wildfires has more than doubled in just 2 decades. Firefighters on the front lines of this crisis have one of the most demanding occupations, exposing them to extreme physical and psychological stress. They endure environments filled with smoke, toxic gases, and high temperatures, which can lead to various health issues, including severe physical fatigue. All these problems can mess with their performance, decision-making, and overall safety. So, what can we do to help protect these heroes? A promising solution would be monitoring their well-being while on duty using wearable sensors. Sounds great, right? Well, it's not that simple. The problem is that existing wearables like fitness trackers fail to endure the high heat, moisture, and intense physical activity firefighters must brave during operations. Plus, to identify complex occupational health issues like fatigue, we need more detailed metrics than just heart rate measurements. That's where the SafeFire project comes in. SafeFire is developing a smart undergarment designed specifically for firefighters. This innovative piece of clothing, made from heat-resistant materials, comes with textile electrodes embedded right into the fabric. These electrodes connect to a sensor that records the subtle electrical signals from the heart. In other words, this wearable can continuously record the firefighter's electrocardiogram, a highly reliable diagnostic tool widely used for assessing heart health. And here's the coolest part, or should I say, the hottest. The system can transmit this data via Bluetooth for real-time monitoring during missions, or store it offline for a post-operation analysis. But hardware is only half of the story. SafeFire also aims to integrate advanced machine learning algorithms to analyze the collected data. These algorithms will help us connect the dots between reported fatigue and physiological metrics, eventually allowing us to develop an automated alert system. Think of it as an alarm going, "Hey, you're about to overdo it," before a health crisis occurs. To truly make this work in the real world, we can't just test our prototypes in a lab. That is why we are working with a group of amazing volunteers that are currently wearing our smart undergarments as they go about their daily tasks. This collaboration allows us to build an authentic database of real-world measurements. By analyzing the data from these real-life scenarios, we can refine our system to ensure it performs reliably under the intense and unpredictable conditions firefighters face. This project not only promises to safeguard firefighter health, but also enhance their operational efficiency, helping protect many more lives. SafeFire is more than technology, it's a lifeline for those who risk everything to protect us. Thank you for watching, and if you want to know more, head to the INESC website and see what other topics the Organic Electronics team is researching.
Para te explicar no... Tenta ver. Estás ao contrário. Tenta agora, o tipo para trás. Yeah.
So, hi everyone, I hope you enjoyed my video.
Oh, wait, sorry. Yeah.
Now I'm just going to clarify a little more what exactly my work is. First, let's recap the objectives of the project. So, we aim to develop a wearable sensor system specifically designed for firefighting environments, enable real-time data transmission via Bluetooth for real-time monitoring, and offline data storage for post-mission analysis, use the collected data to identify patterns of physical fatigue, and create an automated alert system to flag potential health crises early. Now, what is currently happening is our running our prototypes as they go about their daily shifts. Plus, we ask them to fill out a daily activity form where they can detail the type of activity they performed, the intensity of their work, the environmental factors like the temperatures they were exposed to, and their self-reported physical fatigue levels. And this combination of real-world testing and subjective feedback is essential to link the physiological data to the mental and physical stressors. Once the data has been collected, the focus then shifts to processing the ECG signals. And to ensure that only high-quality data is being used for decision-making, it's very important to first filter out the noisy parts. So we take the ECG signal and we divide it into 1-minute segments, and then we classify each segment as acceptable or unacceptable based on signal clarity. Then we calculate the acceptance rate for the entire usage period, and we can use it to reach conclusions about the performance of the wearable. Here's the results that we observed so far. So high-intensity activities led to lower acceptance rates, which was expected due to motion artifacts. And in one instance, we actually saw that reported fatigue correlated with a longer ST interval. However, the data that we currently have is still too limited to confirm these trends, so more data is needed to get more robust conclusions. Moving forward, the project will expand testing to include 40 additional firefighters from both rural and urban settings. The point is to get more extensive and diverse data to be able to compare the performances of the two electrode types that we are testing and identify patterns linked to physical fatigue. Eventually, we can explore machine learning algorithms for automated fatigue detection and get real-time health alerts. In conclusion, this project combines ECG monitoring, smart undergarments, and real-world testing with a focus on fatigue detection. Future plans include larger data sets and machine learning for real-time alerts. And the final goal is to revolutionize emergency response, ensuring mission success and protecting lives. Thank you.
So the project is more focused on firefighters, but do you see it possible in the future to test the algorithms and the sensors to use in other forces or other stress-induced professions?
Okay, so I'll just repeat the question because I was asked to repeat the question. Joanna asked if I could see this applied to other emergency responders, forces, or other applications. For sure, I think any first responder forces like policemen, or even just doctors, honestly, could wear it. I personally, the first other application that I see for this is, for example, for old people, just old people that maybe need constant monitoring but are not physically constrained. So they could go about their daily lives more safely and know that they are being monitored throughout the day. That's the first thing that comes to my mind.
Can I ask you another question?
Of course.
Could you delve a bit further on the methods that you use to obtain your preliminary results?
Okay, so I will elaborate a little more on the methods that I used to get my preliminary results. So maybe I will go back. Back. Okay, so as I said, our firefighters fill out daily forms where they can say how tired they are and what kind of activity that they did. So basically, to reach these conclusions, the first one is very easy. I just went to the forms where they said they moved a lot, and then to the forms where they said they didn't move a lot. And what I saw was that on the days that they did a lot of physical activity, the signal was much more noisy, which is very normal or expected. The other conclusion comes from the features that we get from the ECG signal. So the ECG signal has 5 peaks. So we get the 5 peaks intensities and then the intervals between each peak. And I basically took days where they reported physical fatigue and days where they didn't report physical fatigue. And I noticed that some metrics changed a bit with the reported physical fatigue, namely the ST interval. So that's basically what I did.
I was just wondering, so this is a lot of data if you were to record it all throughout the shift. So do you record it all throughout the shift, or?
We do, yes. It's multiple hours of data. Sometimes 8 to 12 hours of data. Yeah.
So how do you know which sets to analyze?
Okay. So usually I divide it by hours, because if they did physical activity, it wouldn't be for the entire day. So I usually divide it by hours and then analyze each hour and see the parameters for each hour, and that makes it easier. And yeah.
Sorry, we have a question first.
Yes. What's your partner, your clinical partner or medic partner? Because that's, I assume, very well studied, for instance, in cardiac recuperation.
Yes, I don't remember his name, honestly. I know his name is Antonio, but we are working with a doctor to help us throughout this process, yes. I don't know if I answered your question, sorry.
One last one, since we are
Can you already make a prediction how much will a vest cost?
How much will a vest cost? I don't, because I actually don't know the price of the materials that we are using, but I do know that one of our objectives is making this affordable and make it a scalable solution for, especially for Portuguese fire stations, which are not the richest, of course. So we are keeping the cost of the vest in mind.
Thank you very much. And now, now's the coffee break.
Just one second, because okay, so before we go to the coffee break, I just want to say that I believe for the first time ever in this workshop we are way early. So the coffee will start at 10:30 and the session will restart at 11. Please be on time so we keep things running smoothly. Thank you.
So I'm pleased to introduce Tiago Jorge, who is now going to present his project titled Transport Through Critical Magnetic Quantum Dot Away from Equilibrium. This project involves the study of phase transitions in quantum-sensitive systems.
When we look at the world around us, we can see that the same types of matter can exist in very different physical states. The physical mechanisms that describe these phenomena are phase transitions. Phase transitions can separate very different states of matter. The classical example of this is water, which can exist in solid, liquid, or gas phases. These phases are separated by different temperatures. Have you ever wondered why this happens? Well, in simple terms, temperature equals energy, and the more energy a material has, the bigger the disorder of the particles that make it up. For example, the water molecules in ice are aligned like a crystal. But if we heat it up enough, the thermal energy increases so much that the particles become erratic and no longer want to be aligned. Instead, the whole thing turns into a liquid. In physical jargon, we say that as we increase the temperature, the macroscopic order is broken and the system suffers a phase transition. Phase transitions not only occur in water, they're a fundamental aspect of all sorts of matter. And it leads me to talk about quantum materials. While water can be described by classical laws of nature, certain materials, particularly at very low temperatures, exhibit behavior that can only be described by quantum mechanics, that is, the laws that govern every individual particle that makes up the material. For example, if we cool a metal to a very low temperature, we get a quantum state called a superconductor. And this is just an example, as there are many other quantum materials that we know of, like graphene and quantum magnets. These materials and their phase transitions are at the forefront of technology, and their manipulation and understanding is crucial for innovative technologies ranging from levitating trains to quantum computers. In the past, the theory of phase transitions, both classical and quantum, was more or less figured out by some very smart people. However, the best theories that we have are only valid for systems in thermal equilibrium. What do I mean? Well, imagine that I have a body of water and I start shaking it up and down. This system is inherently out of equilibrium, since I'm continuously giving it energy and increasing its temperature. Another example would be if I had a tube of water and connected it to a reservoir on each side held at different temperatures. This would produce convection currents, from the hot reservoir to the cold one, driving the system once again out of equilibrium. This sort of scenario has fascinated physicists in the last years, since it has been shown that by driving quantum materials out of equilibrium, it's possible to create new states of matter. However, there are still many gaps to be filled about the theoretical study of this type of systems. And this is where my thesis comes in. In this project, titled Transport to a Critical Magnetic Quantum Dot Away from Equilibrium, I will pursue a theoretical study of out-of-equilibrium phase transitions in a type of quantum material called a quantum dot. What's a quantum dot? They are essentially very tiny structures produced in a laboratory, which confine thousands of electrons. You can imagine them as tiny islands inhabited by a finite number of electrons. In fact, they are so small that they exhibit quantum mechanical effects. Hence, they are sometimes called artificial atoms. In a laboratory, scientists are able to control these structures with very high precision, making them perfect candidates for studying our type of phenomena. In this work, we will study a quantum dot driven out of equilibrium by being connected to a left and right lead. Both the leads and the quantum dot contain many electrons, with a property called spin, which governs their behavior. If the leads are held at different potentials, these spins will want to jump from one to another, passing through the quantum dot and generating a current. When in equilibrium, this model has a phase transition. Namely, we can distinguish between a disordered and an ordered phase, which functions like a magnet. Now, we want to see what happens to these phases when we vary the potential difference in this new out-of-equilibrium situation. In many regards, our understanding of this sort of systems is still very limited, and if you want to keep advancing the technology of innovative materials, we need to expand on it and find efficient theories to describe them. After all, that's what physics is all about. Ok, vou partilhar o ecrã. Estão-me a ouvir? Está tudo bem? E agora? Posso? Okay. So hello everyone. I will now present my thesis project titled Transport through a Critical Magnetic Quantum Dot Away from Equilibrium. So this project deals with the theory of out of equilibrium quantum matter. And to first introduce it, we may ask the question, what is quantum matter? Well, as mentioned in the video, it consists of any sort of material which must be described by quantum mechanics. An interesting example are quantum dots, which are nanoscale, highly tunable structures which have shown applications in various fields such as spintronics, quantum computing, and quantum sensing. The next natural question to ask is, what does out of equilibrium even mean? And in short, it means that we have a system that can't be described by our usual set of time-independent thermodynamic variables. An example of this is a transport configuration in which a system is coupled to different environments or leads with distinct thermodynamic potentials. These types of systems are very exciting since it has been shown that by driving quantum materials out of equilibrium, it's possible to create new states of matter. And this is where my project comes in. In this thesis, I'll investigate phase transitions of a magnetic quantum dot driven out of equilibrium by a transport setup. Now, I've already talked a lot about phase transitions and quantum dots in the video, so I think it's time to introduce the model itself. So, I'll consider a magnetic quantum dot described by the Lipkin-Meshkov-Glick or LMG Hamiltonian, which captures the physics of a system of n mutually interacting half-integer spins. This model has been extensively studied in equilibrium conditions, where it has shown to have a phase transition if we consider the transverse magnetization, or phi x, as an order parameter, and this is shown in this plot right here. However, it is still widely unexplored in open out-of-equilibrium regimes. And so, to drive it out of equilibrium, we'll connect each spin to a left and right lead, which will be held at different chemical potentials. And so, that's our main model, the LMG quantum dot connected to two leads. Our main theoretical tool to study it will be the Keltish formalism, which is essentially a way to formulate quantum field theories for out-of-equilibrium systems. Using this formalism, we now want to extend the phase diagram of the LMG model to this non-equilibrium regime, and more generally, derive an effective field theory applicable near the transition. The big picture here is that by studying this system, we'll be able to fill in certain gaps in the theoretical framework of these out-of-equilibrium phase transitions, which is crucial to advance our understanding of quantum materials and their manipulation. Now, to wrap up this presentation, I'll just review some preliminary results. So first, I have obtained an effective action to describe the system, and by minimizing it, obtained a self-consistent equation for the transverse magnetization. Now, this equation has revealed some very funny behavior, and in particular, for certain values of the coupling to the leads, we see that as we vary the potential bias in the system, there is a discontinuity in the magnetization. And this could be indicative of a first-order phase transition. However, to arrive at this conclusion, we have to check if the solutions that we found are actually stable, and with that, we'll arrive at the phase diagram for the open LMG model in non-equilibrium regimes, which is a novel result in this area. And with that, I conclude my presentation, and I welcome any questions that you might have.
Hi, so I was wondering if you have any ideas already about critical exponents and universality classes of these transitions, or is that literature on such?
Yeah, that's one of the objectives. So when I say derive an effective theory near the transition, what I mean is that we really want to find an effective phi to the fourth theory, and from that theory extract the critical exponents and universality classes and all that. So that will be one of the final objectives in this project. Right now, we are just trying to see exactly what the phase diagram looks like.
Okay, I'll have a question of my own. What are these quantum dots made out of, and how can they be produced?
So I think I have a slide for that. Okay, so basically to get a quantum dot, we need to have a way to confine electrons in all three directions in a sufficiently small space, such that the material exhibits quantum mechanical effects. And one way to do that is by taking a two-dimensional electron gas in the surface region of a semiconductor, for example, and then further confining that gas by applying a voltage bias in both the X and Y directions. And that will confine the electrons already live on the plane, and then it will be further confined in these two directions so that we can approximate the system as a zero-dimensional system. And yeah, this is one way to obtain this type of structure, and it's usually what we have in mind when we mention this sort of transport scenarios. But the term quantum dot can also refer to other types of systems that exhibit similar behavior, like trapped single molecule systems, for example.
Okay. Thank you for the presentation. We are ready for the next one. Thank you, Tiago.
Thank you.
who will present her project on the designing and modeling of plasma reactors with the aim of producing oxygen molecules from carbon dioxide molecules.
Magnetic tapes were once a cornerstone of sound storage, used in everything from
Hello, my name is Inês Santos, and in the next few minutes, I'll be telling you about my master's project which will be developed at Instituto Superior Técnico on the topic of CO2 conversion. To get it right out of the way, let's start off with a few concerning metrics about this blue-green planet we call home. Global temperatures have been rising, with each passing year being warmer than the latter. It is adamant to tackle the main sources of global warming to ensure a prosperous future for humanity and for the health of our planet. It is well known and documented how the accumulation of the so-called greenhouse gases is responsible for entrapping large amounts of solar radiation. While not the only wrongdoer in this story, carbon dioxide is mainly accredited with the most vexing effects on climate change, biologically attributing to the trapping of solar radiation in our atmosphere. It is also a byproduct of most human activities. Think the burning of fossil fuels or your car exhaust. Despite the unfortunate scenario, scientists and corporations work tirelessly to remove this compound from our air, our soil, and our oceans. Most usual methods include carbon sequestration and storage from carbon sources for large periods of time. But what if it could be possible to not only remove this gas from the air that we breathe, but we could also convert it into a much more desirable gas, oxygen? And, with a bit more work, what if we could use the conversion of the CO2 molecule to bring pure oxygen fluxes to a strange environment, say Mars? Terraforming the red planet is an adventurous challenge that includes modifying its atmosphere to accommodate human necessities. And, with its high concentration of atmospheric CO2, it is an excellent candidate for a new chapter in humanity's history. However, while oxygen can be easily accessible through the CO2 molecule, the process of breaking its chemical bonds is extremely difficult and requires large amounts of energy. In this project, we'll be looking at plasma as an energy vessel to break the CO2 molecule, producing a mixture of carbon and oxygen in various configurations. This path offers versatility, high scalability from laboratory environments, heightened sustainability, and an on-and-off technology which is vital to diminish energy costs and concerns. Plasma reactors can be easily assembled, but the oxygen must be separated from the resulting gaseous mixture to be viable and measurable. We'll be looking at oxygen-permeable membranes built from mixed ionic electronic ceramics, MIEC, to selectively produce flows of O2. These materials are versatile, easy to produce and resistant, and coupled with plasma, offer the perfect conditions for thermodynamically challenging reactions to occur at a lower effort. 3 different ceramic compositions will be investigated, all with a perovskite structure. BSCF will be particularly interesting as it presents a double layer in a dense porous configuration, to compete with the trade-off between oxygen permeability and sensitivity. The membranes will be produced from mild powders and sintered at large temperatures into a small disc to achieve solid diffusion, which will then be investigated using SEM. XRD will also be used to identify the formation of the perovskite compounds at various points along the way. Once assembled into the main reactor, it will be possible to measure oxygen fluxes and to study the efficiency of these methods. The reactor was simulated using a mesh-generating program, as shown here, and it will then be assembled experimentally. By tuning the methods used for producing the membranes, we'll investigate the possibility of achieving our most valuable breathing gas from CO2, and possibly to open doors for further space exploration. Conseguem me ouvir? Ok, a câmera aparentemente não funciona, portanto, espero que dê para ver ao menos bem os slides. Conseguem ver? Ok. Posso começar? Certo, ok. So, hello everyone. As you have seen in the video that was shown previously, my name is Inês Santos, and I'll be developing my master thesis on the design and modeling of a plasma reactor for the production of O2 from the conversion of CO2. As we've seen, from the video a couple information, so this small presentation will just add onto it, and also a few developments that have already been done in the lab. So this work is being done in collaboration with CTN, with Professors Nuno Pinhão and Professor Marta Dias, and so a few preliminary results will be presented here. Starting off with the motivation and methodology that will be used in this project. As we have seen in the video, the motivation is quite simple. We simply want to reduce the concentrations of atmospheric CO2 on the Earth's atmosphere, which is directly related to the intensification of the greenhouse gas effect, which directly relates with climate change. This is quite a simple motivation. However, breaking the CO2 molecule is not an easy task because of the high energy that exists between the molecular bonds, specifically between carbon and oxygen, as we can see here. So this high energy requires specific technologies to break the CO2 molecule, which sometimes require large amounts of energy. In this project, we'll be looking at plasma as the energy vessel to break the CO2 molecule in order to produce carbon and oxygen in different configurations, mostly CO2, CO, and oxygen. In this case, the plasma discharges give us a few advantages comparing to, for example, thermal decomposition of the CO2 molecule, and gives us the correct amount of energy that is needed to break these molecular bonds. Along with this project being helpful on Earth, in this case to reduce the concentrations of CO2 and to produce oxygen, we can also use it in strange environments, for example, in Mars, which has a very high atmospheric CO2, and this could be used in terraforming efforts in order to produce pure oxygen fluxes on the Mars's atmosphere. In this case, we want to couple the plasma discharge with oxygen conducting membranes to isolate the oxygen and to make these pure oxygen fluxes. So these membranes must be produced and must be analyzed in the laboratory. We'll be using a MEAC configuration, which is a type of material with mixed ionic electronic properties that transport the oxygen from one side to the other using its partial pressure as a driving force. And we'll be looking at 3 different configurations, LCCF, LSCF, and BSCF, where each of these letters represents a different compound that is in these membranes. They are produced from the original powders, which are grinded and milled into the sizings that we want, and then they are produced using different techniques. LCCF was produced using a co-precipitation method, as we can see here from the experimental apparatus, which then yields the kind of disc-like membrane that we see below. LSCF is produced in a simple mechanical pressing method where the powders are inside this stainless steel molds and pressure, and then go to be sintered at an oven at a large temperature. In this case, we were able to produce various samples, but all with a fracture along the edges, as we can see in the picture here. So further methods have to be employed in order to understand why this is happening. And in BSCF, we'll be using a tape casting technique using a binder and a dispersant, which you can see here. And in this case, we want to achieve an asymmetrical configuration to fight between the trade-off between oxygen permeability and sensitivity. As for the membrane characterization, we'll be using SAM and XRD to identify the morphology, the structure of the membrane, and also the presence of the desired chemical composition. SAM was used extensively for LSCF membranes, but so far we could not identify any solid diffusion. As we can see from the pictures, the surface is not uniform and the pores are very big and not well connected, so the structure needed to transport the oxygen is not present. Oh, I see. The time is over. Okay. Sorry. Mm-hmm. Yeah, okay. So at this moment, since it's a proof of concept that we want to achieve the pure oxygen fluxes, we are focusing on that mostly, but later on we'll be looking at the carbon. So as I said, we've produce different configurations. One of them is carbon monoxide, which is produced from breaking the CO2 molecule. And in this case, the carbon monoxide can be integrated into different systems. For example, could be integrated with water and hydrogen to produce different types of fuels, for example, syngas. And we'll be looking at, later on, we'll be looking at a way to integrate the carbon in order to, or in this case, the carbon monoxide, in this case, to produce sustainable fuels, even though the main point will be the production of oxygen. And this is also a concern to us because the membranes will accumulate the carbon over time, so this will have to be accounted for.
Our next speaker, Inês Martins, will be taking us to one of the frontiers in particle physics and explore the anomalous events in highly energetic, extensive air showers at SWIGO.
On the high plains of Chile, where the Atacama Astronomical Park is located, the promise of new means to explore the universe is on the horizon. The Southern Wide-Field Gamma Ray Observatory, or SWGO. This observatory is still in development. Nonetheless, it shows great potential for the study of high-energy charged particles and photons arriving from space, commonly known as cosmic and gamma rays. The interactions of particles with low to moderate energies are well understood, as these have been well studied in colliders on Earth, like CERN, providing us with a very precise standard model of particle physics. However, at extremely high energies, the processes behind these particles are more enigmatic. Through the study of cosmic and gamma rays, we may be able to uncover some of the larger mysteries regarding their origins, as well as the physics behind them. The study of cosmic and gamma rays at observatories like the SWGO is performed through the analysis of air showers. But what are air showers? These occur when a cosmic ray particle, such as photons, protons, or other nuclei, interacts high in the atmosphere, cascading into multiple secondary particles. Particle production then continues in a repeating cascade process until reaching a critical energy, after which the intensity of new interactions attenuates. This phenomenon is what we call an extensive air shower, with the secondary particles that reach the ground being what the SWGO will actually detect. The main difference between gamma rays and cosmic rays are the particles produced in the shower. Gamma rays generate electromagnetic showers, where mostly electrons, positrons, and new photons are produced, while cosmic rays create hadronic showers, where hadrons, like pions, are present, in conjunction with electromagnetic showers and other particles. The SWGO itself will operate as a ground-level particle detector, in line with other current generation observatories, like the HAWK and LASSO. It will monitor energies from 100 GeV up to a few BeV. This surface detection technique is based on water-Cherenkov detector units placed in a grid. Inside these units, the shower secondary particles interact with water, producing Cherenkov radiation, which is then detected. This allows for a duty cycle close to 100%, which, combined with a large high fill factor core, promises a significantly better sensitivity than other observatories. Even so, there are some trickier aspects to this detector, as it only relies on ground particles to distinguish between electromagnetic and hadronic components, with a part of the shower's information not being detected. This is why the current development phase of the SWGO, when protocols for the detection and identification of air showers are established, is one of the more challenging. As previously stated, in most showers, the number of particles produced reaches a maximum corresponding to a critical energy. This, however, is not always true, as in rare cases, the stochastic nature of the shower interactions may produce more than one peak in the shower profile. The anomalous shower events, as they are called, can be a result of different factors, such as particles that interact closer to the surface or to secondary particles that retain most of the primary particle's energy, amongst other possibilities. The study of these events can thus provide significant insights into the physics behind the shower development. These anomalous showers are in fact the basis of my project, as I'm set out to characterize features of these showers at the surface, relating them to their longitudinal development with the aim of improving current methods for gamma-hadron discrimination, a crucial step in the protocols of observatories like the future SWGO.
First, we need to hear from Ines, which of course will present remotely. Hi, Ines.
Hi, so do you see my screen, right?
Yes.
Okay. So, good morning, everyone. Hope you're ready to hear me talk about my project on the characterization of anomalous air showers events in the SWGO. The main motivation for my project comes from the importance of discriminating between gamma and hadronic events while working within the constraints of a surface detector, like the future Southern Wide Field Gamma Ray Observatory, or SWGO. It is especially important to study anomalous events as they may provide significant insights into the physics behind the shower development. Overall, my project will be a significant part in the careful development of the procedures for the discrimination of gamma and cosmic rays reaching the observatory, which are essential for future studies of these phenomena. Through the use of state-of-the-art simulations, I will be able to characterize shower features at the ground level for my project. I'll start by establishing the framework for the project and acquiring the simulation data that ranges from 100 to 200 TeV. Then I'll build on top of the existing C++ code to perform the analysis of the data. The first steps of this analysis will be to recreate the plots obtained in here that were created in previous simulations that are based on some important parameters for gamma-hadron discrimination that I show in here.
Sorry for interrupting, Ines. Your presentation is going beautifully, but would you try to go full screen? Or yeah, we are seeing your slides.
Yeah. But then it comes.
But then it comes back to.
Okay, just select slides on the left.
Yeah, great. Yeah, that's perfect.
That's okay.
Proceed. And sorry for interrupting.
I'm sorry. Okay.
It's fine.
So as I was saying, from all of these, the more important is the FR mean, as it is the more interesting for us to study. So along with these plots that I have here, I'll produce also the cumulative distribution of the FR mean. The shower development parameters, the Xmax and E0, which weren't analyzed in the previous simulation, will also be a focus of my project. So after investigating the relations between the FR mean and other parameters, the results obtained will then be used to improve the gamma-hadron discrimination and identify rare showers. Through the characterization of these rare events, a reduction of the gamma background can also be accomplished. Finally, I will focus on establishing a potential link between the anomalous air showers and the hadronic multiparticle production properties of the first interaction. The ability to find such a connection could be helpful in the development of a selection criteria for anomalous showers. There is also an interest in the determination and study of deep penetrating showers, with their numbers expected to be correlated to the effective cross-section of the interaction of the primary particle. With all of this, we expect to establish the connection to the longitudinal development of the shower and to better understand the formation of rare and anomalous events, leading to the improvement of the current methodologies used in the ground-based gamma-ray observatories, such as the future SWGO. And with this, I finish my presentation, and I'm ready for all of your questions.
Thank you, Ines, for the very nice presentation. I was so eager to hear from you that I almost hit your pitch. Are there questions from the audience?
Okay, would you elaborate on the variables that describe some features of the shower, like FR mean or X max, for example?
Okay, so as I said, the most important for us to study, and it's kind of the focus of my project, is the FR mean. The FR mean is basically is a ratio, is a very simple equation, is the signal of the shower in the detector that from radius above a certain R mean, a certain minimum radius, over the total signal of the shower. And this characteristic is very interesting because of the way that showers that are hadronic in nature, like the ones, the proton showers, proton showers, they tend to have more, it tends to be a different value of FR mean because there is more signal that is lost at the higher radius. So it ends up creating a distinction in theory between gamma and hadronic showers. So by studying the FR mean, we could be able to produce a better discrimination factor than what we use right now for the NS mu and N mu that are the signal of muons that reach the ground in events that can be confused between gamma and hadronic showers. So this kind of parameter is not yet been well studied. That's why we think that by testing it, we can develop new methodologies for it.
Okay, thank you very much. Sorry for interrupting you. Let's thank the speaker once again.
So our next speaker will be Tomás Baltazar, whose work with the Snow Plus experiment focuses on the event pileup identification and rejection.
If you've ever heard of the Snow Plus experiment, it is most likely because of its ambitious search for the neutrino stable beta decay, the experiment's primary goal, which had the potential to revolutionize our understanding of neutrino physics. However, the Snow Plus experiment is not limited to a single objective. Rather, it encompasses a wide variety of exciting goals in neutrino physics, including detecting neutrinos from the sun. Thanks to the deep underground location and the low energy threshold, it is able to measure the flux of low energy solar neutrinos. These measurements will help our understanding of neutrino-matter interactions and provide new insights into solar neutrino oscillations. Studying antineutrinos from nuclear reactors in Canada and the US. Nuclear reactors produce large numbers of antineutrinos, which Snow Plus can detect. This offers an opportunity to study neutrino oscillations in even greater detail, advancing our understanding of this fundamental process. Detecting geoneutrinos from within the Earth. Snow Plus is sensitive to antineutrinos produced by beta decay in the Earth's crust. These measurements could help better understand the role of nuclear decays in generating Earth's internal heat flow, specifically from the decay chains of elements like uranium and thorium. Capturing neutrino from supernova. If a supernova occurs within our galaxy, Snow Plus could detect the neutrino burst it produces. This would enhance our understanding of supernova mechanics and provide valuable data on neutrino behavior under extreme conditions. But how does Snow Plus detect these events? All of this is possible thanks to the design of the Snow Plus detector, which is located in Sudbury, Canada, deep within a mine over 2,000 meters underground. This location provides critical shielding from cosmic muons, reducing the background to very low levels. The detector consists in a 6-meter spherical acrylic vessel, AV, filled with an active medium. Surrounding the AV is a photomultiplier tube support structure, PSUP, which holds nearly 9,500 photomultiplier tubes, PMTs. Most of the PMTs face inwards to detect the events happening in the AV. Additionally, a smaller number of PMTs face outwards to detect external sources of light, such as muons. To further reduce the background, the space between the AV and the PSUP, as well as outside of the PMTs, is filled with ultra-pure water, shielding the detector from radiation emitted by the PSUP and the surrounding walls of the mine. All these features enable SNOW+ to achieve very low levels of background noise. However, in order to meet its goals, the experiment requires an even greater sensitivity. One particular type of background we want to eliminate comes from pileup events, which occur when two events happen so close in time that they are reconstructed as a single event. My project focuses on developing techniques to identify and reject such events, further reducing the background levels. By addressing these challenges, we're helping SNOW+ move closer to achieving its extraordinary goals, advancing the frontier of neutrino physics and deepening our understanding of the universe.
Okay, can you see it full screen?
Yes, we can.
Perfect.
Okay. Okay. So hi everyone. My project is pileup event identification and rejection in SNOW+, enhancing the signal to noise ratio. So I've talked about pileup events, but now I'm going to go more in depth in why it is important that we study them. In the SNOW+ experiment, we have a trigger window of 460 nanoseconds. And as I've mentioned, if two events happen in the same trigger window, they'll be reconstructed as a single one. This has two major consequences. First, their energy will be summed, which means that two events that before reconstruction had an energy lower than the region of interest can now fall within it. The other is that the volume where the reconstructed event is can be different from the volume of the original event. So what can we do about pileup events? We started by identifying a set of variables that would help us reject them, and we ended up choosing two, beta 1, 4, which classifies events depending on their isotropy. Single events are isotropical, so they'll have lower values of beta 1, 4, while pileup events, because they are a combination of single events, will have higher values of beta 1, 4. The other variable was near AV, which classifies events depending on how close they are to the surface of the AV. If a event is close to the center of the detector, it will have a value between 0.4 and 0.5. With these variables established, we then study the effect that a cut on them would have on the Monte Carlo data, and we also calculated the survival ratio. Once we were satisfied with the results, we then applied these cuts to the data and we observed their effect. So after the Monte Carlo simulations, we ended up with the final cuts beta 1, 4 smaller than 0.1 and near AV bigger than 0.3. And as you can see in table 1, this leaves us with a very high survival fraction for the single events for small fiducial volumes. So since these results all agreed with our expectation, we then decided to apply the cuts to the data. And here are two examples of the histograms that we got. On the left, you see an histogram for the region where only pileup events should be. And when we analyzed it, we saw the spectrum of combinations that included pileup events from bismuth and polonium. And on the right, it's an histogram for the region where only single events should be. And when we analyzed it, again, we saw only the spectrum for the single events of the bismuth 210 and proctactinium 234. As we expected. So we concluded that the cuts that we applied could satisfactorily separate pileup events from single events. In a very quick summary, what we did was we found the cuts that would optimize this rejection of pileup events while minimizing the sacrifice ratio of single events. And these cuts were B214 smaller than 0.1 and UAV bigger than 0.3. In the future, the events that were in this project identified as pileup events should be further analyzed and the results should be compared to expectation. Thank you.
Are there any questions from the audience? Oh, okay, so I'll start by asking you about the two variables you introduced to us, the beta 14 and near AV. Could you please elaborate a little bit more on what they represent?
Yeah, sorry if I wasn't clear. So I think I can show you some plots, like, for example, this. So these are the histograms for B2 and 4. And again, it classifies how isotropical an event is. And on the left, you see an example for a pileup event, and you can see it not only it has a lot of events that have a B2 and 4 value bigger than 0.1, but it's all over the place. It's not a uniform distribution. While on the right, you see the histogram for a single event, and most events are all have all a value below 0.1, and it's all also very uniform. On the near EV side, I can show you these two histograms. And the reason why we introduced the near EV was because, as I've mentioned I can just go back to the first slide. So here you can see that events that are close to the surface, they can be reconstructed near the center of the EV. And this is a very big problem for us because near the surface is where we have most contamination and most backgrounds. So when we do an histogram of the fiducial the volumes that are in the inner detector, for example, as you can see on the histogram on the left, we get a very high concentration of events that have a value of the near EV bigger than smaller than 0.3, which correspond to these types of events.
Okay. Thank you for the explanation, Tomas. And everyone, please give a round of applause.
In our universe, there's matter and antimatter. However, neutrinos are a neutral particle, so are they their own antimatter counterpart? Our next speaker and dear friend, Manuel Abreu, will be talking about neutrinoless double beta decay at SNO+ to try to figure this out.
Particle physics explored the fundamental particles that make up our universe and the forces that govern their interactions. Generally, each particle has an antiparticle, a counterpart with the same mass but opposite charge. Among these particles, we have neutrinos. They are incredibly small, electrically neutral, and interact weakly with matter. But much about neutrinos remains unknown. For instance, we know they have mass, but we don't know the value of that mass or even how this mass is generated. And perhaps most intriguingly, if particles and antiparticles have opposite charges, but neutrinos are neutral, could they be Majorana-like particles? If yes, then the neutrinos and the antineutrinos would be the same. Neutrinos most commonly appear in nature through a process called beta decay. In beta decay, an unstable nucleus transforms into a more stable one by emitting a beta particle, an electron or positron, and a neutrino or antineutrino. In rare cases, single beta decay is energetically forbidden, so certain isotopes undergo double beta decay, where two beta decays happen simultaneously. This results in the emission of 2 electrons and 2 antineutrinos. Now, if neutrinos are their own antiparticles, something interesting could happen in double beta decay. The 2 neutrinos could annihilate each other, leaving only 2 electrons in the final state, which will carry all the transferred energy of the system. This process is called neutrinoless double beta decay, and observing it would provide strong evidence that neutrinos are Majorana particles. Not only would this help explain the nature of neutrinos, but will impact other fields of physics such as cosmology. To search for neutrino stable beta decay, a very rare event not yet observed, we rely on a large detector with a very high radio purity. SNOWPLUS, the follow-up of the Sudbury Neutrino Observatory, is one of them. It is located 2 kilometers underground in a mine in Sudbury, Canada, with shields from cosmic rays background, and has a large mass of about 1 kiloton of liquid scintillator. Thanks to the complex cleaning system, SNOWPLUS has achieved high levels of purity, around 10 to the minus 17 grams of uranium per gram of scintillator, minimizing background noise and enhancing sensitivity to neutrino stable beta decay. In 2025, in order to search for the neutrino stable beta decay, SNOWPLUS will begin loading tellurium into the liquid scintillator. Tellurium contains tellurium-130, the most abundant isotope known for undergoing double beta decay, with an endpoint energy of about 2.5 MeV. This key value defines the region of interest for neutrino stable beta decay in tellurium-130. Since there are no neutrinos in the final state, in the case of a positive observation, we expect a peak at this energy. However, before adding the tellurium, it is critical to study potential background events that could hide the neutrino stable beta decay signal. Using current data from SNOWPLUS, I analyze events within a 3.3 meter radius from the scintillator center to minimize the contribution from external noise, such as events coming from the detector components. My analysis focuses on identifying the background events in the neutrino stable beta decay region of interest and on tuning variables to reject them, ensuring this region is as clean as possible. At the same time, I make sure that the sacrifice of potential neutrino stable beta decay events is as low as possible. By doing so, I pave the way for detecting a clear, unambiguous signal of neutrino stable beta decay. Good morning, good afternoon. My name is Manuel Abreu, and in this presentation I will focus more on the part of my analysis. And my analysis had two main purposes. The first is to identify a clear period of data, and then the second is to apply to that data a series of cuts and variables to reject background events. So, the first thing is note that, as I said earlier in the video, any events that fall within this region of 2.5 MeV are background events, okay? And one of the main radioactive backgrounds is bismuth-214, which has a beta decay, so presents a beta spectrum from 0 to the 3.3 MeV of energy. That's the end point of the decay. And this makes bismuth alone very hard to identify. So fortunately, we know that it is immediately followed, the beta decay of bismuth, it is immediately followed by a beta decay from polonium. And by alpha decay, sorry. Being an alpha decay, it's very easy to identify it. So our strategy to identify, it's based on the coincidence technique. That is, first we look for a polonium event, and then after identifying it easily, we look back in time for coincident events and say that there are candidates to bismuth. To this identification, we analyze the efficiency, and it's found to be 80%. This analysis for the efficiency is with Monte Carlo, and is important to study the activity. So now we can study the bismuth activity. Just a note that there was a period in which they were filling the acrylic vessel with the liquid scintillator, and this is the analysis of the bismuth activity after that filling period. So here is the first 40 days, And we can see there's a spectrum, and we fit the spectrum with an exponential and a constant. From the constant, we extract the uranium concentration, and from the exponential parameter, we extract the half-life, the radon half-life. So we conclude that radon was in the detector, and we discard the first 20 days of the analysis to this, because of this conclusion. So now I cut from the data, I applied a series of cuts to the data, and after each cut, it was evaluated the sacrifice of that cut, that is, the fraction of neutrino stable beta decay events that cuts, rejects, and you verify that after each cut, all the events, the remaining events, were uniformly distributed. Thank you.
Thank you, Noel, for the presentation. Are there questions on the audience? No. So I would like to ask you, why did you find radon in the experiment? Were you expecting it?
Yes, that's a good question. So just a note that radon. Radon itself is not, let's say, dangerous. The problem is that radon is in the decay chain, and later on that decay chain, that's our bismuth that we want to reject. Okay. So why radon? Radon has a problem that it's a gas. And being a gas, a radioactive gas, the gas particles infiltrate basically everywhere, and it's very hard to clean it. So after a period of loading the scintillator, many experiments looking for this decay expect to find radon concentrations after a period of filling the scintillator.
Okay, so on another note, you say you try to achieve the best sacrifice possible, meaning to preserve the better results. What is your best cut, meaning the cut that has the least amount of sacrifice? Right?
Yeah, so, yes. So, here are the sacrifices, and I want to highlight the first one, the BIPO cut. BIPO means bismuth plus polonium, okay, together. And this cut is with the identifications that I talked earlier about. Just note that since it has a very small sacrifice, and we want to reject more events of BIPO events, we enlarge the conditions so that we could cut even more BIPO events with less sacrifice. That's it.
What's your efficiency on detecting the bismuth? And how could you measure it?
So here is with Monte Carlo. We simulated bismuth events, and it's the number of the events that passed all these conditions over the number of generated events from Monte Carlo simulations.
Okay, from Monte Carlo. But perhaps in that data that you have.
From the data.
Because you have radon that is producing the bismuth, so perhaps you can go there and scavenge for that.
Yes, so like calibration, more or less.
Yeah.
So there is no. SnowPlus has no, let's say, active calibrations, but there's some verifications from the data that we can look some regions that have characteristics events, but there's no method of calibration, let's say that.
Okay, thank you. Let's thanks the speaker once again.
I'm pleased to introduce our next speaker.
Whenever we drive along a highway, we pass by structures like tunnels and sound barriers designed for safety. Portugal, like many other countries, is facing an urgent challenge: generating clean, renewable energy. Highways, with their vast and underutilized infrastructure, offer an innovative opportunity to address this need by integrating photovoltaic panels. However, identifying suitable locations for these installations is far from straightforward. My name is João Tavares, and my research tackles this challenge head-on. The title of my thesis is YOLO Application on Portuguese Highways for Photovoltaic Energy Potential Evaluation. Using YOLO, a state-of-the-art computer vision algorithm, I aim to automatically detect and identify highway structures and assess their potential for solar energy generation. YOLO, first proposed in 2015, is a groundbreaking object detection algorithm leveraging convolutional neural networks to detect objects in real time. Unlike traditional multi-stage detection methods, YOLO combines region proposal and classification into a single unified neural network, drastically reducing computation time. The algorithm divides an input image into a grid, with each cell predicting bounding boxes and class probabilities directly. Its confidence score is calculated by combining the class probability with the intersection over union, which is a measure of the overlap between the predicted and the ground truth bounding boxes. The versatility of YOLO has made it invaluable in domains where both accuracy and speed are critical. In healthcare, it assists in tasks such as lesion detection and brain tumor segmentation. In industrial applications, it is employed for surface inspection processes, identifying defects and anomalies. Its adaptability extends to various sectors, showcasing its robust utility. However, training YOLO is no small feat. Achieving high precision values requires a substantial number of annotated images, which are often unavailable online due to the time-intensive nature of manual labeling. To overcome this challenge, data augmentation techniques are employed, allowing datasets to be artificially expanded without the need for additional images. These techniques involve applying transformations such as rotations, contrast adjustments, and cropping, which enhance the diversity of training samples and improve model robustness. This helps YOLO learn faster and better, making it more reliable in real-world applications. But to offer you a preview of the progress made in this research so far, my model has successfully predicted the detection of sound barriers with corresponding confidence scores. This result highlights the potential of the YOLO algorithm to accurately and efficiently identify complex structures, showcasing its applicability in real-world scenarios. By accurately identifying suitable highway structures and evaluating their potential, this research aims to transform these infrastructures into renewable energy hubs, contributing to a smarter and more sustainable future.
So, hello everyone. Did you know that highways could become a new frontier on renewable energy? Imagine sound barriers and tunnels, structures that we pass by every day, acting as solar energy hubs. My research, YOLO application on Portuguese highways for photovoltaic energy potential evaluation, will try to turn this vision into reality by showing how highways can become and tackle this new challenge. So the world is facing an urgent challenge, the need to find sustainable and clean energy solutions. And so highways, with their vast and underutilized infrastructure, can present an innovative opportunity to address this need by integrating photovoltaic panels. Structures like sound barriers or tunnels that were designed mainly for noise reduction and safety could be transformed into more efficient and dual-purpose solar energy hubs. So this is where my research steps in. I will use YOLO, which is a computer vision algorithm that enables me to automatically detect and identify these highway structures and then assess their potential for solar energy generation. So YOLO is renowned for its speed, accuracy, and computational efficiency, because being a single-stage detection method, it combines not only region proposal, but classification into a single unified neural network, making it ideal for real-time and large-scale applications. So the first steps of my research were to implement some data augmentation techniques on my original dataset, and then these augmented images were then used to train my YOLO V10 nano model that is specifically designed to predict sound barriers. As you can see from the results, they were very high promising because the model already achieved a precision of 86%, a recall of 89%, and a mean average precision of 91%. These results not only highlight the model's accuracy, but also the effectiveness of this approach, and also the ability to scale this to more structures. So think about a system that could map thousands of miles of highways and pinpoint every single structure that is capable of supporting photovoltaic panels. And so with this research opens the door to smarter and greener highways. By combining this artificial intelligence with renewable energy, we can redefine these infrastructures in order to serve dual purposes, not only to enable transportation, but also to generate renewable energy. And so the next steps of my work will be to scale this model in order to identify other highway structures, assess their potential to the for solar energy generation, and to further optimize the model. And so, every time you go by the highway, just look at what surrounds you, and you will see an amount of solar energy potential surrounding you. Thank you for your time.
Thank you for your presentation, João. Are there any questions from the audience? Oh, I saw 3 hands.
First of all, great presentation, I think, great project. But what are the main limitations of YOLO?
My main problem here with YOLO is that I don't have a much large data set. So this is why I need to implement some data augmentation techniques, because there's a very time-consuming nature in manual labeling these data sets. Because so you can see that the images from, exactly, this is, so first of all, when I start, this is raw data, so there's no bounding boxes there. So what I need to do is that manually, I need to draw a bounding box in every single sound barrier that exists here. So think about 20 sound barriers in the same image. I need to do that 20 times, and the bounding box needs to fit perfectly the dimensions of the sound barrier in order for there not to be any bias to the model. And so this is very time consuming, and because this is something that requires normally a lot of people to do that, in the research papers, there's not any available data set with already annotated images. So this is probably the major limitation.
Any more? Okay, there's 3 more hands. We'll go from left to right. Oh, sorry.
Okay. So what tool did you use to do the annotated image?
Okay, so I use the RoboFlow tool. This tool is very good because it not only enables me to do these drawing boxes to annotate the images, but also enables me to apply directly the data augmentation techniques that I use. So some rotations and some contrast adjustments, which allowed me to expand my data set that began with 40 images, more or less, to 96 images, just from the data augmentation techniques.
Okay, there are still 2 more. One was from...
Yeah. So I have one small question, which is how are you going to use tunnels for this? And the other one is how do you assess the impact on potential for photovoltaic energy? Because you don't only need the barrier, you need it to be exposed to the sun and so on and so forth.
So all the measurements that are going to be made to calculate how much solar potential these structures have will be by using the PVLib package of Python that not only gives me which is the amount of energy that I can possibly get with these structures, so giving the radiance and the slope that they have, but also it will give me what is the correct panel that I can use, because we have many panels, different panels, so it's going to give me what is the best panel that I can use for these specific structures. For the tunnels, it is not yet detailed how they can become with installed these photovoltaic panels, but it will be probably this upside, because there are a lot of electricity connections inside the tunnels, and so they need to get this electricity from the surroundings, and this is an opportunity for them to automatically and independently get that electricity just from the solar.
Thank you, João, for your nice presentation. We will now head for a lunch break and we'll be back by 1:30 p.m.
Projeção. Mais alto.
Vocês não viram este filme, pá, mas
Good afternoon, everyone. Thank you for coming today. I am more than pleased to introduce our next speaker, Margarida Pereira, who has been working on reduced models for relativistic plasmas using particle and cell simulations and machine learning. This work proposes to further understand astrophysical plasmas, one of the most remarkable phenomena in our universe. So let us start.
Plasmas, hot ionized gases of electrons, positrons, and ions, govern the behavior of cosmic structures across vast spatial and temporal scales. Understanding the various processes that govern these plasmas means understanding the observable universe. While traditional plasma physics provides robust frameworks for non-relativistic systems, astrophysical environments require novel methods to be described. Kinetic models excel in simulating phenomena like turbulence and reconnection, but their computational intensity limits their use in multidimensional systems. So emerging data-driven techniques offer a promising solution to generate these reduced ordered models for exotic plasmas. There are many machine learning algorithms that will result in accurate descriptions of dynamical systems, like neural networks. But a lot of these are opaque or black box models. We aim to use a method that provides interpretable and reduced equations to describe our systems, allowing us to understand the underlying physics. In this work, we employ the sparse identification of nonlinear dynamics, or SINDI, algorithm. SINDI is a procedure of taking time series data and extracting systems models that describe this data. Sparse regression takes advantage of the assumption that most dynamical systems can be modeled by a sparse set of terms. To obtain the data and simulations in this work, we will be using OSIRIS, a massively parallel, fully relativistic particle and cell code. PIC codes are a widely used numerical tool for simulating plasmas from first principles. The PIC method works by self-consistently solving the equations of motion for all the particles in a discretized spatial grid. Because the PIC method does not apply fluid or collective approximations, it is ideal for studying kinetic scale effects. To understand how SINDI works, let's look at the example of a Lorentz system. If we only have access to data from the system, we know that there are governing equations, but we don't know what they are. We can measure the state of the system, so every row is a measurement in time. The simplest thing would be to model this dynamical system using a 3x3 matrix, but we know that a linear model is not going to capture the rich dynamics of this Lorentz system. So what the SINDI algorithm does is it augments the right-hand side to include nonlinear terms in addition to the state itself. And now, with a constructed library, the entire objective of SINDI is to try to find the fewest terms in this library of candidate dynamics that describe the equation of state. Sparse regression fits the data using an extensive pool of candidate terms, but ultimately selects only a sparse subset that best describes the system. The sparse regression problem is then formulated as finding the weight vector xi that optimally solves our differential equation. SINDI approximates the system's dynamics as a linear combination of candidate terms, selecting only the most relevant ones using a sparsity enforcing cost function, balancing accuracy and model complexity through a regularization term. This model can be changed, and a few options are already implemented in SINDI. This is useful, for example, when we have a nilpost problem with many correlated variables. We can choose a regularization method that will adjust to this data and produce better results. In this study, we apply a weak formulation of sparse regression, so instead of selecting measurement points, we select small spacetime volumes from the simulation domain and integrate both target and basis quantities to mitigate the effects of noise. This was shown to be crucial in a 2022 paper by Alves and Fusa. The central challenge in sparse regression is constructing an appropriate library of candidate terms, as the set of possible expressions is infinite, and an excessively large library means problems. To test the sparse regression approach, we decided to apply it to data from a 1D PIC simulation of two counterpropagating electron streams undergoing the electrostatic two-stream instability. Moving forward, our goal is to harness both the power of PIC simulations and sparse regression to extend our work to thermal relativistic plasmas. Of the universe exhibit complex phenomena that makes it harder for us to model them, especially in relativistic systems. So particle and cell simulations are crucial for capturing the detailed behavior of these plasmas, but due to their computational intensity, we can't use them in a lot of large multi-scale systems. So fluid models are an alternative, but these require accurate fluid closures in order to capture the detailed kinetic effects. So we aim... Sorry.
Who's next?
Okay. So we aim to use the sparse identification of nonlinear dynamics, or SINDI algorithm, in order to produce equations that are interpretable. And this is done by choosing select terms from a big library of candidate terms. So we decided to test this sparse regression framework by applying it to a well-known classical system, the two-stream instability. And here the objective is to infer the kinetic Vlasov equation, which models the evolution of our distribution function. And in fact, by applying SINDI, we are able to get this two-term equation, specifically the two terms we wanted, with an around 3% error. Additionally, we wanted to validate this equation by performing a Pareto optimal analysis, where we can see the balance between model complexity and accuracy through this graph here, and we can see that it confirms our two-term identification. So now that we've confirmed that we can use this sparse regression framework, we want to apply it to our thermal relativistic plasmas, which are more complex and less explored regimes. So here we start out with our Vlasov equation again, and we want to integrate it to obtain higher order fluid moment equations. But this system of equations is not closed, and in order to close it, we need an expression that relates pressure and internal energy. But this is not trivial to obtain in this regime. So in order to be able to do this, we're going to be following a simplification model, the water bag. So the water bag makes it so the distribution function is constant between boundary curves and zero everywhere else. And this simplification allows us to more easily analyze our Vlasov equation and integrate it to obtain microscopic fluid quantities, including the heat flow, which in this case is exactly zero. And it's this that allows us to find our extra equation to close the system. So with this work, we were able to review previous work in extreme plasma physics, focusing on sparse regression applications to big data. And in the future, we plan to extend this sparse regression framework for thermal relativistic plasmas, starting with our water bag model. We'll be collaborating with UCLA and applying for GPU hours in order to support the computational demands. Thank you.
Okay, thank you everyone. Are there any questions from the audience? Okay, because I have two. One of them is what you presented your work about using sparse regression. Why not use other methods such as neural networks or?
So, as I said in the video, we can use neural networks and other deep learning methods to get the explanation for the systems. But it's basically, as I said, a black box model. So we have an input and an output, so we know what the system is like at a certain point that we want, but we don't know how the algorithm got there. It doesn't show you the equations behind it, it's a convoluted method, so it's not good for gaining an intuition of what's really happening physically. So sparse regression is a much simpler algorithm, and from there we can really, or try at least, to see what's happening in our system.
The other question that I had was, well, you presented your work and now in the end you prefer the magnetized plasmas.
Mm-hmm.
What are the difficulties that you need to overcome? Why include it not here?
Mm-hmm. So right now, the biggest challenge with the relativistic magnetized plasmas is this a very unexplored system or domain. So we're starting with a water bag model because it's more simple, because we have an analytical equation that we can compare it to, and we can more or less know what to include in our library of candidate terms. But for magnetized plasmas, a lot of times we have no idea what's happening, or we don't know where to start, so it'll be much harder to make this library of candidate terms. That's going to be our biggest challenge.
Thank you very much. Are there any others? Thank you. You may ask one question. Fast, please.
I will. Okay. I've seen this presentation before last Friday, and I've seen Margarida answer some tough questions. So my question is simple. Compared to the work of Alves and Fuse, from what I understood, what you do is simulate the same physical system, but applying the sparse regression. Is that it, or are there additional contributions?
In the Alves and Fuse paper, they are applying sparse regression. So what I've done here was basically recreate the results, but I did some additional testing to see what the limits of the sparse regression are. But now moving forward, we want to expand on it and start with relativistic systems, which they haven't explored yet.
Okay, so now I ask a round of applause. Okay, our next speaker is João Pedro. He is one of my best friends and I am more than excited to introduce him. He's working on mean field theory to combine two different approaches for plasma physics, and I guess that who's better than him to present his work. So.
Between them. They are responsible for many interesting phenomena, such as cosmic ray acceleration. Cosmic rays are accelerated in astrophysical scenarios and contain some of the most energetic particles that we have ever observed. But how can this happen? The main mechanism behind cosmic ray acceleration are collisionless shocks. These occur when two counter-streaming plasma flows interact with each other, forming instabilities. Collisionless shocks are not easy to study. In these scenarios, we have microscopic instabilities that influence the macroscopic dynamics of the system and vice versa. When we zoom in supernova explosions, for example, we find small-scale fluctuations that induce an anomalous resistivity. This will slow down the plasma, forming the instability that mediates the shock. Therefore, anomalous resistivity is a phenomenon that occurs due to small-scale fluctuations and impacts the large-scale behavior of the system. To study anomalous resistivity, we can either take a kinetic approach, where we consider all the particles of the plasma, or a fluid approach. While the kinetic approach takes into account the fluctuations, kinetic simulations are very expensive. On the other hand, fluid simulations are ideal to simulate large-scale systems, but they don't capture the anomalous resistivity. This brings us to a new question. What if the anomalous resistivity was taken into account in fluid simulations? To do this, we would need a description of anomalous resistivity that uses only fluid quantities. To do so, we can start with fluid kinetic simulations, since we know that these capture anomalous resistivity. We apply a mathematical formulation that separates fluid quantities from the fluctuations. Applying this to Ohm's law, since we know that anomalous resistivity is manifested as an electrostatic potential, we can find an extended momentum equation that takes anomalous resistivity into account. While the left-hand side of this equation is just the momentum equation for fluid quantities, the right-hand side contains the anomalous resistivity. We were able to assess that the pressure and density fluctuations are the main quantities that drive the anomalous resistivity, and that this result is independent of the resolution of our simulations. This is a breakthrough for simplifying plasma models. But this doesn't end here. We want a description of anomalous resistivity as fluid quantities, and not averages over fluctuations. To do so, in the future we plan to use machine learning tools such as neural networks to recover a formulation of anomalous resistivity that can be incorporated into fluid simulations. With the fluid description of anomalous resistivity, we will shorten the scale gap that exists nowadays and be a step closer to a multi-scale description of plasma. influence the whole dynamics of the system. For example, anomalous resistivity. Anomalous resistivity is manifested as an electrostatic potential and it comes from fluctuations, small-scale fluctuations that occur in these collisionless shocks, and they mediate the shock that is going to be propagated through the whole system. While we can do kinetic simulations that capture these, kinetic simulations are really expensive, and fluid simulations, which are good to simulate large-scale systems, do not capture the anomalous resistivity. To do so, we started this project with the goal of combining these two models, a fluid approach and a kinetic approach, and do a fluid approach where we take small-scale fluctuations into account. To do so, in this PIC2, we started by defining these three objectives. The first is verify anomalous resistivity in shocks. The second is to obtain a model for it, and the third is to identify the physical quantities that dominate this phenomenon. To start, we needed to obtain the electrostatic potential. So we had to start from Vlasov's equation and recover the momentum equation. We were able to assess that they have matching profiles, but these fluctuations are due to the fact that kinetic simulations simulate particles, a finite number of particles, and not the Vlasov equation, which treats plasma as a distribution function. After this, we applied a mean field theory by separating these quantities into their fluid quantities and their fluctuations. So this means the fluid quantities that are simulated in fluid codes and the fluctuations that drive this anomalous resistivity. By doing so, we were able to define this model, which is just a momentum equation for fluid quantities that is simulated in fluid codes. And this right-hand side is a combination of terms that are responsible to the anomalous resistivity that we are looking for. We then compare each one of these terms with the left-hand side, and we were able to conclude that the anomalous resistivity can be reduced to only these two terms. These plots show that these two profiles actually match really well. Oh. In the future, since we obtained a model for anomalous resistivity as fluid quantities, we cannot implement it directly in fluid codes, but that's our final goal. So we want to use in my thesis machine learning models such as deep neural networks to obtain a model that can be incorporated into fluid simulations. With this project, we were able to assess that we can actually find anomalous resistivity from particle in cell simulations, and that the pressure gradients and the density fluctuations drive this anomalous resistivity, which makes sense since these shocks are propagated due to instabilities in the density of the plasma. For the next steps, we want to do an MHD approach, which is basically combining all the species in the plasma in order to obtain a model that takes into account the fluctuations that are made by each one of the species, these protons and positrons, and find this anomalous resistivity. As we said before, then we want to use machine learning to solve this problem.
Okay, thank you very much, João. Are there any questions from the audience? Okay, because once again, I have two. João, you said earlier in your video, and you emphasized that result as a breakthrough. So what do you mean by the results were independent from the simulation?
Okay, so
the resolution?
We did fully kinetic simulations. I think I have here. Oh, yeah. And these are made by simulating the particles of the plasma, and we did a lot of runs. So we simulated with different box sizes, we simulated with different number of particles, and we were able to recover the model for the anomalous resistivity in each one of them. And in all of them, the profiles match really well. The only difference is by increasing the number of particles, particle in cell codes converge to the Vlasov equation. So when we obtain the electrostatic potential, these profiles start matching even better.
Okay, your results were remarkable, and I thought that you could extend them for other effects. Will that be possible? Can you generalize this approach for other things?
Well, we can, and you can take more fluctuations into account, but in this work we want to only capture how transverse fluctuations influence the longitudinal dynamics of the plasma. So we define this mean field theory as a transverse averages so that we can capture this phenomenon and not others, for example, statistic fluctuations.
Okay, thank you very much for your presentation. So our next, so okay. Okay, our next speaker is Mafalda Rodrigues. She is working on a very exciting field in physics, which is nuclear fusion, and she's trying to use deep learning methods for that matter. But obviously, once again, who could better present it than Mafalda? So I'm just introducing her.
Proposal: application of deep learning to reflectometry signals in nuclear fusion plasmas. As global energy demands keep rising, our dependence on fossil fuels is becoming unsustainable. These energy sources are not only limited, but also have serious environmental and health consequences. That's where nuclear fusion comes in. It has the potential to generate massive amounts of clean and sustainable energy. In fact, when fusion occurs, that is, when two light atomic nuclei combine to form a heavier one, it releases nearly 4 million times more energy than burning fossil fuels. One of the most promising fusion reactions is the deuterium-tritium one. But to achieve fusion, we need to overcome the Coulomb barrier, which is the electrostatic repulsion between positively charged nuclei. One of the best ways to do this is by heating plasma, a hot ionized gas made of deuterium and tritium, to extremely high temperatures, increasing its velocities, making fusion possible. But simply heating the plasma isn't enough. We also need high densities, so the probability of fusion increases, and strong confinement, to keep the plasma stable. That's why tokamaks are so important. These donut-shaped devices use powerful magnetic fields to confine the plasma, preventing it from touching the walls, which can damage the reactor, make the plasma lose confinement, reducing its energy and temperature, making fusion impossible. So, the control of the shape and position of plasma is essential. That's where plasma diagnostics come in. And one key technique for this purpose is microwave reflectometry. Reflectometry works by sending electromagnetic waves into the plasma. These waves reflect when they reach a layer with a specific electron density, which is directly related to their frequency. In the reflectometer, the reflected signal is mixed with the reference signal, allowing us to strike a spectrogram of the bit frequency. This is then converted into group delay values, and by selecting the peak with the highest intensity, we can determine the final curve. Applying Abel inversion, we obtain the position of each density layer, giving us the electron density distribution. However, this process isn't always perfect. Noise from the system, plasma dynamics, and the characteristics of the reflectometer can distort the data, making it difficult to obtain a reliable group delay curve, adding errors to it. Previous methods, like the best bet algorithm, helped improve the curves, but were too slow and required human supervision, making them unsuitable for real-time plasma control. However, to truly capture the correct electron density distribution, we need a more reliable way to extract the group delay curve. This is where deep learning comes in. Our goal is to develop a deep learning model that takes reflectometry spectrograms as input and outputs an accurate group delay curve. This will enable faster, real-time plasma control, bringing us one step closer to making nuclear fusion a viable energy source. And now, let's hear from the real Mafalda, who will explain, in more detail, the steps of the work that we want to develop.
So I'm the real Mafalda, and before we dive in on the next steps, let's just recap the goal of this project. So we want to use spectrograms of the reflectometry signals to obtain more reliable group delay curves and thus obtaining more representative density profiles. We will improve the accuracy of plasma control systems and of course support the broader goal of making nuclear fusion more viable. But how? Well, we want to create a deep learning model that uses as input our spectrograms of our sign-offs and as output our group delay curves. And in order to do this, we first have to choose an architecture to our model. And in the field of sign-off analysis and focusing on spectrogram analysis, there are two major architectures being developed and used: the convolutional neural networks and the transformers. They are based on two fundamental concepts. The first one, convolutions. Model use local fields that can capture local features within the sign-off, and attention mechanisms allows the model to focus on the relevant parts of the sign-off and is able to capture the long range patterns within the sign-off. A basic convolutional neural network uses convolutional layers, but we can actually enhance its performance by adding attention layers. However, the transformer is based only on attention mechanisms. And because in this project we want to start with a simple model and try to refine it based on its performance, we will start with a simple convolutional neural network and try to improve it, and at the end try to have an approach based only on attention by using a transformer. And to do this, we will first start to create a dataset by using the real density profiles, but wave simulations to actually get the refractometry sign-up. We are using this synthetic data to train and test our model under realistic but controlled conditions, which enable us to actually explore our architectures. Of course, that our ultimate goal is to validate them with real sign-offs coming from the as-accept tokamak. And finally, the question is whether it would be possible or not to real test these models in real-time experience, since our goal is plasma control. And in conclusion, and trying to answer this question, scientists say yet again that nuclear fusion is a few years away. Are they right this time? By trying to improve our plasma diagnostics with deep learning and having a better control of it, we are trying to make this future a reality, so maybe they will be right.
Yeah, okay. So, real-time monitoring and control. What kind of timescales are required to receive the signal and automatically change the plasma shape or position to keep things stable?
So, what we want to achieve is in the scale of nanoseconds. But the thing is that previous work using convolutional neural networks in projects similar achieved like a microsecond range. So we are trying, that's why I said that we were trying to use the most simple model possible. So maybe just start with a simple convolutional neural network with just one layer and try to improve, but always thinking in mind, of course, the trade-off between time and and performance.
Are there any other questions from the audience? You are more than welcome to ask. Mafalda already asked herself more questions. So. I have one that I could ask to one of the speakers, to one of the other speakers, but I'm going to ask to you. So, people are using AI for several things. Why do you need it in this case, and what is making it better for your approach?
So if you come back here, when we talk about the group delay curves, and we do as I explained in the video, we do the error inversion to obtain our density profile, we actually should use monotonically group delays, but in real life, we don't have it. So you can do two things. If we smooth our group delay before the error inversion, or we can try to smooth our density profile after the error inversion. But this is usually done in a supervised way, which takes a lot of time, as we know. And because we are talking about real-time plasma control, we want to automate it and make it a little bit more faster. That's why deep learning is so important.
Thank you for answering. Can I ask one other question, please? You mentioned somewhere, I don't recall, that you were trying to use synthetic data. Yeah. So how are you planning on obtaining them? What's your opinion on that matter? Yeah, I guess it's...
It's actually a good point because it will be a little bit time-consuming, this zero step, because in previous works with reflectometry and our plasma densities from the Architects Upgrade tokamak, there were a lot of simulations in one dimension, but because we are trying to have a more realistic sino and have motivations both in phase and in amplitude, we want to use two-dimension simulations, and because of that, we cannot just invert the process of I have a density profile and then I will do the inverse process and get our sino. We also have to consider magnetic flux surfaces, which makes it a little bit more complicated. But yeah, but at the end we have a more realistic sino. That's what is important to us.
Okay, thank you very much for your answers and for your presentation. Please, a round of applause. Okay, our next speaker is Marco. Okay, where is Marco? Okay, he's there. Okay, Marco is working in astrophysical plasmas. He's trying to use particle and cell codes and experiment. And, well, he is also trying to understand it. So let us see what Marco has been doing. Let us start by his video. So let's go.
Accelerating things? As humans, we have made great efforts to accelerate particles at nearly the speed of light, or even make planes fly at supersonic speeds. But did you know that nature has already mastered the art of acceleration on a scale far beyond anything we can conceive? Hey, my name is Marco, and I'm here to tell you a bit more about this. Let us first take a step back and talk about shocks. Shocks can be found in all kinds of environments in the universe. If an object moves fast enough through a medium, it will cause that medium to pile up, compress, and heat up. As a result, a shock wave is formed. Supersonic jets, for instance, compress the air in front of them so rapidly that a shock wave is formed, which we experience as a sonic boom when it reaches the ground. Another example occurs in outer space. When stars run out of fuel, they collapse inward, unleashing a huge explosion that pushes out a cloud of gas and dust, the so-called supernova remnant, at thousands of kilometers per second, generating also a shockwave. However, in outer space, things work a bit different than on Earth. There, particles are too far apart from each other for collisions between them to be the ones mediating the shock. They rarely even happen. Instead, charged particles feel each other's electromagnetic field from a distance, mediating what we call a collisionless shock. The high compression and temperature of a collisionless shock front makes it a very interesting zone, with lots of instabilities capable of amplifying local magnetic fields. When particles cross this shock front, they bounce off these amplified fields, gaining more and more energy, up to a point where they just break away from the shockwave and fly off into the galaxy. This process, called diffusive shock acceleration, makes collisionless shocks in supernova remnants some of the most powerful particle accelerators in the universe. For instance, they are one of the main sources of cosmic rays, which are just accelerated particles traveling through the universe, acting as space messengers and bringing physical data from distant parts of the cosmos. Interestingly enough though, collisionless shocks aren't just limited to supernova remnants, they also exist much closer to our home. One example is the Earth's bow shock, a shockwave created as a solar wind, which is just a stream of charged particles coming from the Sun, collides with Earth's magnetic field. Despite knowing a lot about it, some mysteries remain. For instance, observations of shock-accelerated particles rely heavily on the radiation they emit while moving, the so-called synchrotron radiation, which is mainly emitted by electrons. But electrons aren't the only particles accelerated. What about ions? Do they gain energy from this process as efficiently as electrons? We're not quite sure. Another problem is the so-called injection problem. How can electrons enter this energization loop if they don't have the energy to cross the shock front in the first place? We know fairly well how they gain energy once they're in, but how do they get in at all? This brings us to the main point of my work, studying how these shocks are so effective at accelerating particles to such incredible energies. To find out more about this, we just cannot rely only on observations, since they can resolve for smaller scales, so we will rely on two other tools. The first one are particle in cell codes. These are computational simulations that model how charged particles and electromagnetic fields interact. By solving Maxwell's equations and the motion of individual particles, we can simulate and study collisionless shocks down to the smallest of scales. And the second one is laboratory experiments. Laboratories like the National Ignition Facility use some of the most powerful lasers ever built to create miniature astrophysical shocks in a controlled environment. This lets us measure shock dynamics in real time, offering valuable insights that complement both simulations and observations. So, by making use of both of these tools, I intend to shine some light on how these massive particle accelerators work. Well, there you have it. I hope this sparked a bit of curiosity about my research, and if you have any questions, feel free to reach out. Thanks for watching.
So, hi everyone. As you saw, the title of my work is Study of Shockwaves in the National Ignition Facility, NIF. So, let's get into it a bit further. As you might have taken from the video, collisional shocks, like the ones here represented in the left, are mediated by binary collisions between the particles in a medium. However, shocks also occur in astrophysical plasmas, like in settings represented here. And actually here, the particle density is so low that particles rarely collide with each other. And so these shock waves cannot be mediated by binary collisions anymore, but rather by electromagnetic interactions between these particles. These shocks take place in places like supernova remnants, like here in this section in specific right here. And these happen really far away from us. But the thing is, they are some of the brightest events in the universe. And when we actually look at them and the radiation they emit, we see that it follows the power law with an index of around -2.7. And this takes us to one of the main reasons on why studying these shocks is important. Because when we do the same to cosmic rays that arrive here on Earth, when we look at their energy, we see that it also follows a power law with an index of around -3, up to really high energies of the order of 10 to the 16 eV. And this is a really important observation because it leads us to believe that collisionless shocks are one of the main mechanisms behind the acceleration of cosmic rays. We do know how these particles are accelerated in these shock fronts. They just bounce around in it, as you saw in the video. But this poses a really big problem for electrons because their thermal energy shouldn't be enough for them to cross the shock front in the first place, because it is of the order of the ion-Lama radius, which is much, much bigger than it. So they need a mechanism that pre-accelerates them to take part in this whole process. And this is known as the injection problem, and it remains open until today. Namely because probing the microphysics of these things is really happened since they happen really far away from us. But luckily there are a couple of tools that we can use to study these things. The first one is numerical simulations, with a special emphasis on particle in cell codes. And the second one is laboratory experiments taking part in high-power laser facilities like the National Ignition Facility, which are really important because they allow us to study a scaled-down version of these things in controlled conditions. And this takes us exactly to the goal of my thesis, which is to use numerical simulations to guide and validate upcoming laboratory experiments, namely one that's going to take part in NIF later this year, and to study problems like the injection problem. And to do that, I started by conducting a 1D simulation on a particle in cell code with parameters that are relevant to this experiment. And when we do that and we look at this data, we see that the electron charge density as a function of position shows the formation of this structure, which is actually a shock front. And we do the spectrogram of the energy of these electrons, we see that they do get thermalized up to some energy, as you can see by the good fit to the data of Maxwellian. But for higher energies, we see more and more counts, which proves that electrons are indeed being accelerated in NIF conditions. And this takes us to the conclusions of my work, which is it should be possible to observe the formation of magnetized shocks in NIF, as well as particle acceleration. But more work remains to be done, namely conducting 3D simulations, since these experiments will take part in a 3D setup. And also study the injection problem and the electron acceleration in different shock configurations, since I only covered one. That's all. Thank you.
once again asking for questions for Marco. Okay, thank you very much, Professor. Feel free.
Okay, I also seen this presentation last week, just as with João Pedro as well. Did you use realistic parameters from MIF?
Yes.
Okay. So, what was my question? What was the power that you simulated? You mentioned it's one of the most powerful lasers in the world.
Yeah, the power it has shows in the power of creating plasma acceleration, or not plasma acceleration, of colliding two streams of plasmas with really high energy. So in there, they collide plasmas in the order of, with a velocity in the order of 1,000 kilometers per hour. I simulated this stuff with a velocity of 0.2 c. Like it's.
I mean the laser parameters. Did you get those parameters, or do you get secondary information?
No. But the thing is, the high power in the laser is useful to create this setup where we have two plasma flows counter streaming.
So you start from the plasma parameters.
Exactly.
Okay.
Exactly.
Okay, fair enough.
For me, this was like an initial condition. There, they use really high powerful lasers to get things moving.
Okay.
Okay. I have one question that I would like to ask. So, Marco, how long does your simulation take? This is the first part of the question.
Yeah, maybe locally in my computer in 6 CPUs, 50 hours, I think.
Okay, wonderful. So, instead of spending all that time, I saw recently that CERN is using machine learning algorithms to fast simulation for calorimetry.
Yeah.
So I was wondering, why couldn't you apply that knowledge in here?
Because you can. The thing is, you can't just cross out particle in cell simulations because only kinetic theory gives us detailed information on the onset of these instabilities in the shock front. And machine learning is indeed a powerful tool to make sense of some of these data, but you really need these simulations to generate the data and to be a proxy to these collisionless shocks, since they are so far away from us. But after having the data, sure, you can use machine learning to try to make some sense out of it, yeah.
Okay. Do we have time for other? Yeah. Okay, so Marco, by the way, congratulations. I saw that you recently won one of the most prestigious grants to study at Johns Hopkins. So I have this question, it's just a curiosity. What does this have to do with work you're going to do at Johns Hopkins? Because they do not work at plasmas, so do you think your knowledge in plasmas can be useful, for instance, for the next plasma-driven accelerators? So something like that.
Okay, so what has my work here has to do with the work there. I mean, when you look at it from a broader point of view, the short answer is nothing, absolutely nothing. But the thing is, the grant that I won is to work in a specific laboratory where I'll be studying the motion of cancer cells and developing physical models to try to predict how they move. So the equations that I derived here and the tools and the results that I got to here are not directly useful there. But the thing is, I'll be tackling whatever problems I'll be tackling there with the tools that I gained from working in this stuff. And I think that working on this stuff gave me a pretty big box of tools.
Yeah, so you can kind of apply that knowledge in this to tackle this different problem. Yeah, that's wonderful. Thank you very much for your presentation.
Thank you.
Just another round of applause, please. Okay, so my final introduction is for João Cândido. Cândido has been working on improving the computational efficiency of simulations, so this kind has to do with my last question for Marco. In a sense, we are kind of using the same questions, and now we'll be addressing this problem. So let us hear from João.
Of high-field fusion plasmas. Most of the visible universe is a magnetized plasma, from the vast intergalactic medium to the dynamic magnetospheres of stars and planets. Studying plasmas is essential not only for understanding the cosmos, but also for addressing practical challenges, such as developing fusion energy, a clean, nearly limitless power source based on the same principles that fuel the stars. However, before fusion technology becomes commercially viable, one critical challenge remains: effectively confining the incredible hot plasma required for fusion to occur. One promising solution is the magnetic mirror. a device that confines plasma between regions of strong magnetic field. These fields act to reflect particles, preventing their escape and maintaining plasma stability. To advance this technology, we need efficient tools to simulate highly magnetized plasmas. Simulating plasmas in a fundamental way often relies on particle-in-cell or PIC algorithms, which model particle interactions through a self-consistent electromagnetic field evaluated on a grid. While powerful, these codes face a major challenge: simulating the interaction of complex nonlinear processes across a vast range of scales. This challenge is particularly pronounced in highly magnetized plasma. Charged particles spiral around magnetic field lines in a process called gyro motion. The radius of this motion, known as the gyro radius, shrinks as the magnetic field line strength increases. For instance, in the magnetic mirror experiment WHAM, the gyro radius near its coils is 1,000,000 times smaller than the size of the reactor. Simulating both the microscopic gyration of particles and the macroscopic behavior of the plasma requires enormous computational resources, well beyond what is currently feasible. My research addresses this problem by implementing an efficient simulation algorithm based on the Guiding Center Approximation, or GCA for short, which simplifies the plasma dynamics by averaging out the rapid spiral motion of particles, focusing instead on the center of the particle's orbit. This approach retains the essential physics of the system while avoiding the need to resolve the gyro radius in every calculation. By significantly reducing the computational cost of PIC simulations, this approach makes it feasible to study highly magnetized plasmas in greater detail. During my thesis, I intend to implement and study the validity of this algorithm in comparison to the standard approaches. Then, to apply this algorithm to simulate the behavior of plasmas in magnetic mirror devices like WHAM. To sum up, my research leverages the Guiding Center Approximation to address a great challenge in plasma simulation: the vast separation of scales in highly magnetized systems. By improving the efficiency of simulations in these extreme conditions, this work could accelerate advancements in both fusion energy and our broader understanding of plasma physics. Thank you for watching. Hello, my name is João Cândido. I'm here to present about my project, Kinetic Simulations of High-Field Fusion Plasmas. It's important for us to study highly magnetized plasmas so we can understand important phenomena in our universe like relativistic black hole jets. But on the other hand, nuclear fusion has long been regarded as the flagship application for these magnetized plasmas. Fusion promises clean, safe, and nearly inexhaustible energy production using the same principle that fuels the stars. In the last few years, with the development of high-temperature superconductive coils, there has been a lot of interest in the development of high-field fusion reactors. An example of this concept is the magnetic mirror, which confines particles in between regions of very strong magnetic field. Here we have WHAM, an experimental high-field fusion mirror that will serve as a proof for this concept. Simulations, particularly kinetic simulations, are very important for the development of these devices since they allow a very fundamental description of the plasma. However, they face a major challenge, which is how to capture the interaction between complex nonlinear phenomena across a vast range of scales. This separation of scales is particularly difficult for highly magnetized plasmas because charged particles spiral around the magnetic field lines in this motion, which is the gyro motion. And the radius of this motion gets smaller as the strength of the field increases. If we take WHAM as an example, this radius will be 1,000,000 times smaller than the size of the device. So it's very difficult to simulate the microscopic aspects of the plasma and also capture the collective behavior. To address this, we will use the Guiding Center Approximation, where we average out the dynamic of the particles over the gyro motion, so we can focus instead on the center of the orbit. This allows us to keep the essential physics of the system while not having to solve the gyro frequency at every step. During my thesis, we intend to implement efficient high-field kinetic simulations based on the guiding center approximation. So we want to implement this algorithm, and we predict that for WAMP, our algorithm will need 20 to the power of d plus 1 times less computational steps than conventional approaches, where d is the dimension of the system. Finally, we intend to implement the algorithms that we develop to study magnetic mirrors. Thank you very much.
Okay, thank you very much, João. Okay, you raised your arm. Any questions, Miguel? Oh, okay, that's Are there? But you could ask a question if you want. So, are there any questions from the audience? Okay, Professor.
Yeah. So you focus your research in the case of what are they called, those linear devices?
Magnetic mirrors.
Magnetic mirrors.
Yes.
Are the values comparable? For instance, the electron gyro rate, is it comparable to the case of tokamaks, or is it many orders of magnitude different? I mean, is your research also applicable to the case of tokamaks, for instance?
Yes, the magnetic fields involved will be in the same order, so yes. However, I'm focusing on this linear geometry because I'm using Osiris and it's not made for toroidal geometries.
Okay, I have a question. Well, excellent presentation. But I was wondering if there is any trade-off, because you are saying that you are making an approximation to minimize the time. So, what are you losing anything or any kind of information? What's
Yes.
the trade-off?
I'm using an approximation, so we're losing the information about the scales lower than the gyration frequency. And the disadvantage that we are not using a completely fundamental approach, like the usual particle and cell codes that basically are guided by the Maxwell's equations, and here we are using approximation. Another disadvantage of this is that the guiding center approximation is not always valid. So if the fields change much faster than the gyro frequency, this approach is not valid, so we cannot use it. But it is a way to go around this, is that we can actually dynamically change the approach that we use. So you can use the standard PIC codes, and when we can't use the guiding center approximation, and then when we need to have these very magnetized plasmas that are very difficult to study, we can change to the new algorithm.
Yeah, so you combine the best of both worlds.
Exactly.
Yeah, that's wonderful. Thank you very much for the presentation.
Thank you.
And for answering the questions. Just another round of applause.
So, hello everyone, I'll be your chairperson now. My name is Gonçalo, and I would like to kindly introduce you to Vasco Santos, who has been working on the potential of the use of magnetic interface system in bidimensional graphene. So, a round of applause to Vasco.
The evolution of science as we know today comes from many different ways, but all of them are driven by the human will to push further and try to find new ways to engineer new innovations in order to unlock new phenomena. And with new demands, new materials are needed, and therefore more research is needed. But in order to exploit the more exotic properties that these new front-end materials possess, we need to understand how they behave and find new creative ways to apply them in new devices. In my master thesis, I am interested in the study of charge transport at atomically thin materials, known for showing some intriguing characteristics. But how or where can we find any of those rich dynamics and phenomenology, normally in collective systems and particularly in liquids? But would electrons form a fluid? The answer is yes. Back in the late 60s, Soviet physicist Radi Gurji showed that, under the right circumstances, electrons in a conductor are indeed a fluid, which is known as the Gurji effect. However, for that to happen, a delicate balance needs to occur. The collisions between electrons need to be very frequent, quickly leading to an equilibrium distribution, but at the same time, the collisions between electrons and other impurities or other quasi-particles need to be scarce, so that the momentum is mostly conserved. But for many years after that theoretical discovery, the Gurji effect was very observed in very low temperatures, which made the task of implementing it in some sort of technological innovation way more difficult. But recent years of research have shown that there are materials that actually exhibit that kind of fluid transport on ambient conditions, namely the so-called Dirac materials. And you most certainly know at least one example of those: graphene. We can then focus on graphene as a fairly strong candidate to develop technology and explore interesting phenomena related to electrohydrodynamics. For instance, one can envision how a graphene field effect transistor, or just GFET, can be used for high-frequency communication and detection of radiation. The thing is, GFETs are already known devices, but since the electronic fluid responds to electromagnetic stimuli, an interesting case of study would be to observe how they behave when a local change in one stimulus is imposed, like for example a magnetic interface. So, what's the goal? We propose to study the system around the magnetic interface, set in a GFET, which can be achieved through a dual-gate system with reverse external magnetic fields, or resorting to the intrinsic magnetization of the substrate composed of two magnetic domains. The electronic flow from each side will interact at the magnetic interface and develop charge waves very localized and sometimes chiral, that is, that can only propagate in one direction. Using both analytical and numerical methods, we explore the possible solutions of this scenario and their properties, hoping that, in the future, such propagation modes can be used for signal propagation on a waveguide, just like this video is getting to you through optical fiber and copper cables. A particularly exciting feature of some of the modes is that they are topologically protected. This means that they possess and conserve some kind of charge that makes them quite innocuous to defects and decay, which is great. I mean, we all know that if the propagation is assured, you will always be able to watch this awesome video without problem. But this is only a small scrape on what can be discovered about these modes. The next step? Stay tuned.
So, hello everyone. Well, I'm not gonna explain you again what I'm doing because, well, it's on the video, you already know. So, I'm just going to give you the details of what I'm actually working on. And I'm going to do this in a, let's say, a simple three-step method, which is how am I approaching it, what have I done, and what I want to do in the thesis. Well, everyone starts the model. And if you look at those equations, congratulations, you have yourself a plasma. So, graphene, plasma, that doesn't make much sense, but well, since we are in hydrodynamic transport, we can use a fluid description. And well, you have the magnetic field there for the interface, and we are going to include this whole viscosity, which is not conventional. Well, so now I have to define how the field actually works. And the way of doing this, it's not very straightforward, because ideally you would have something like this, some kind of step function, very abrupt, whatever, but if you all took calculus and you know that doing things that are not continuous are, well, they're not good. So we're going to use this smoother version that actually accounts for, let's say, the smoothness of, let's say, the limitations of the nanofabrication processes. And well, what I did is pretty much just work with these simplified model, linearized equations, very standard in plasma physics. And yeah, I have some some solutions. For some reason, the GIFs are not well functioning, so whatever. But I want you to take attention to this one, which is pretty much the, let's say, non-propagating, longitudinal, no vorticity, and it does not dissipate. So it's actually pretty good for communication. However, when we start with a viscid case, that unconventional viscosity that I have mentioned, well, things get uglier. And if the GIFs were working, which they are not, everything that you're seeing here would pretty much just crumble to the sides. And so this is not good. Still. But well, if you're not convinced about the work, well, we crunch the numbers, we compare this with, well, our theoretical work, with our numerical simulations, and well, we good. So the next step is just to say, what do I want to do? Well, for a viscid case, things became a lot harder, so I didn't actually get to extract as many solutions. So another step that I want to take after that is to go to more complex regimes. So linearizing is not that much complete. And just to end this in a high note, well, of course, those GIFs I wanted to show you, they are, well, they are still a bit ill-defined. I want to work a little bit more on that. But still, all of this work shows that there is a lot of potential on these kinds of systems. And yeah, questions?
Thank you very much for the presentation. There's any question? No? Okay. Oh, okay. So, please.
Vasco, just one question.
Yes.
What's the typical dimension of that transition region between the two?
Okay, so let's say the G factor as a whole would be, if we have, let's say, commercial size things, you can have from like 1 micron total to, let's say, half a centimeter. So we would expect that width of the well, which I mark there with those green dashed lines, to be just a few nanometers wide. So we can actually achieve a good, let's say, confinement of the charge in that region, and therefore improve the speed of transmission.
Okay, I have one question. Nobody wants? Okay. So you mentioned all viscosity, right? But there's other kinds, right?
Yeah.
So why do you neglect them?
So there are a number of reasons for that. Firstly, our goal to build this device in real life, we would not actually consider, let's say, the deformations of the material itself. So considering, let's say, shear stress would not be that much important. And other thing that is very important for this viscosity is that in the energy levels, let's say, that we are working with, it does actually depend on the profile of the magnetic field. So we actually can't consider this without considering this.
Okay. Okay, I think we are okay for questions. Thank you. So now I would like to call and to introduce you Armando Gonçalves, which is contributing to one of the most sophisticated plasma simulation tools, the Lisbon Kinetics or Loki code, and trying to push the boundaries of plasma modeling.
Have you ever wondered what makes the flicker of a neon sign, the sterilization of surfaces, the efficiency of modern microchips, or even the scientific justifications for seemingly impossible technologies in many sci-fi movies? The answer lies in an extraordinary state of matter, plasma. But not just any plasma. Unlike the searing hot plasma in stars, low-temperature plasmas are way cooler, often near ambient conditions. When an electric field is applied to a gas, the supplied electrons collide with the gas-heavier species, ionizing them. The resulting ejected electrons trigger a cascade effect of further collisions and ionization. Despite the presence of a high-energy electron population, with temperatures reaching 100,000 kelvins. The overall temperature and volume of the plasma is primarily determined by the denser neutral species, which can remain at a low temperature, hence the term low-temperature plasma. In the plasma soup, this high electron temperature promotes a higher collision rate, accelerating reactions and enabling the creation of new species, making the entire process more effective than traditional thermal methods. Inside the plasma, reaction mechanisms unfold like intricate dances between particles, driven by a cascade of interactions. Coupled with the higher collision rates induced by the plasma's energetic electrons, these reactions create a rich environment for chemical transformation and efficiency. Molecules collide, exchange energy, and break apart into fragments, creating entirely new species. To actually start making predictions, we need to understand the rate at which these reactions occur. This is where the rate coefficient comes in. It tells us how fast a reaction happens, and we use it to calculate how much of a species we will get after some time. Usually, most of these values can be found in the literature. However, rate coefficients of reactions involving electrons can be calculated using two critical pieces of information: cross-sections, which essentially tell us the likelihood of a reaction, and the electron energy distribution function, or EEDF for short. The EEDF describes how the electrons in the plasma are distributed across different energy levels. To find it, we often solve the electron-Boltzmann equation. One approach is the two-term approximation, which simplifies the process and gives us a reliable estimate of the EEDF. Once we know the rate coefficients, we can simulate the plasma. By solving a system of rate equations, we track how the densities of ions, electrons, and neutrals evolve over time. These simulations allow us to predict and optimize plasma-driven processes with precision. Low-temperature plasmas are more than just a scientific curiosity. From enabling green chemistry to powering the next generation of devices, these plasmas hold the key to a brighter, more efficient future. And it all begins with understanding their inner workings, one reaction at a time.
Hi all. Can I just say a few words before the clock's ticking? Yeah. I just want to say that I'm really touched to be here today with all of you guys here. Like, it was. I'm really nervous, by the way. It was. Yeah, because seeing you guys like surviving those linear algebra classes and now being here doing like high-level research is really touching. I wasn't very close to him. As you know, our colleague who recently passed away. But I think that wherever he is, he's super proud and super happy to see us guys here pushing the boundaries of science and engineering. Thank you guys. So can I ask like a round of applause? Yeah, so that was my intro, so now you can put the clock ticking or whatever.
Okay, Amanda.
Oh, sorry. Yeah, so whatever. Yeah, I'm gonna skip this. This is we growing up.
Armando, wait.
And
you can start. I can put the clock ticking when you want.
Oh, awesome! I didn't know that. Okay, perfect. So yeah, time to get graduated. My idea here today is going to give you a really crash course on the topic that I'm presenting. As you know, it's low temperature plasmas. And at the end of my talk, you can grab here your little certificate. I think I have enough certificates on awesome, cool people to pursue plasma researchers. So yeah. Where is my backpack? Because I have, yeah. I'm taking too long. I'm so sorry, guys. Okay, I have here candies to people that participate. I will probably do some questions, so don't be afraid, okay? I'll just throw you candies. Okay, so let's start. What? Okay, so to our mathematicians and physicists, you can just leave now, okay? So I will do a lot of messed up stuff. Okay, let's start. So we have N2 and H2, and we want to turn it into NH3. What's the idea here? I mean, you can just dissociate N2, H2, and then pray that these guys eventually bond to NH3. Yeah, sure, but there are actually a lot of ways of this happening. I will explain here a very simple reaction scheme, which is this one. Okay, why is this so bad? Oh, man. Yeah, and let's try to see what's the density of NH3 after some time. Okay, to do that, we can see where it's being produced, which is here, and where it's being lost, which is nowhere. We are not using NH3. So our equation of the density over time would be just this, right? With that formula, we have K, the densities, and that's it. Okay, excellent. What would be for NH2? This time we have NH2 being produced here, NH2 being produced here, and also being consumed here. So this would be the equation. I think this is simple. Tell me if not. The same for NH, where NH is being produced here, is being destroyed here. Okay, awesome. And finally, H, which is being produced here and being destroyed here. So here are the formulas. The two comes from there. Okay, awesome. So then we would build this amazing system of equations, and then we can start putting this onto a computer or whatever. Just to do some calculations, let's calculate this KR. I will use like simple values. So can any one of you tell me what would be this K based on this? So you would do just 1 plus 2 plus 3 plus 2 plus 3 plus 1, which is what? Someone? 12, thanks! Thanks, Miguel! Okay, that's precisely it, it's 12. So you would just plug 12, blah blah. It's 12, yeah. And then you would put this into the equation. And then you have the air of production, and you would go from here to solve the rest of the equation. So as you can see, and I'm really finishing, just a simple reaction scheme already gives us complicated things. Now imagine a full, really complex reaction scheme. It's like amazing and it's really complex. And yeah, you have here, I just use neutrals, you can use ions and very, very much things. Okay, so just to top it off, this is the end of the class. You are now graduated, congratulations. I didn't have time for questions, I'm so sorry, okay? But you may ask, okay, what's the next steps? Well, you can contribute to better schemes, you can contribute to the code, you can collaborate in experimental diagnostics, and you can use ML to simplify kinetic pathways, which is the work I'm been doing, okay? So thank you guys for the attention. Wish all the best to your future endeavors. Thank you guys. By the way, you can now retrieve your, I mean, after the questions probably.
Yeah, they need to.
Yeah, sorry.
Yeah, so thank you for the presentation. So anyone has questions? You need to have. So.
I mean, yeah.
Okay.
One thing I missed was, what is the motivation for this?
Really?
This is important.
Yeah, it is important.
You should be able to answer. So apart from the mathematics, the code and so on, there must be an underlying reason why we want to understand better these reactions in particular. So can you explain this in a few seconds?
Okay, this reaction in particular, which is really specific, N2 with H2 giving NH3, is because Well, as I don't know if it was said in the video, but it's mainly because of fertilizers. So this equation is the equation that with our wash process that gives us NH3, which is used on fertilizers, and fertilizers are like top 3 things most important to humanity right now, but also because of hydrogen fuels. So one idea that people are suggesting is bonding H2 with NH to give NH3, so to store it in a more secure way, and then dissociate it again to get H2. And also alternative fuels with NH3 are being explored. So there are a lot of things that use this specific reaction. I don't know if that answers your question.
Definitely.
Yeah, definitely. Okay, thank you. Thank you for the question.
So okay, I think that there's a question there.
I have just one question, if you don't mind.
Yeah.
Wonderful approach. So, what does that certificate can hold in IST?
So as you can see, there's a totally legal certification stamp on it. So I think you can get into my IT with this. So just try, just try. You want a candy, by the way? Thank you for the participation. Thank you, Gonzalo.
Thank you.
I mean, everyone can get candies, I guess. I think I have candies for everyone.
Okay, great job.
Nobody wants
No, you can give them.
Okay.
Yeah, coffee break.
Coffee break.
So, okay, everyone. Now we will have Miguel Pereira, who is interested in the regime of large tokamaks. His work will focus on data from DASDEX, great tokamak, okay, to determine a radial measurements, okay?
Energy is one of the most important concepts of the human story. Initially, tasks would only be achieved from the energy we extract from the food we eat. However, as technology progressed, we learned of all the other places where it could be taken from. We learned how to extract it from wood, in the form of fire, and we learned to extract it from the splitting of atoms in dedicated reactors. Our obsession with shiny fire remains, and we keep burning fuels which are best left underground, where their carbon can't re-enter our atmosphere. Of all the low-carbon ways to generate power, one has remained the light at the end of a tunnel we can't seem to reach. For our current energy sustainability goals, it is much too far, but when we finally unleash it and perfect it, it has the potential to outshine all the other methods. This is fusion energy, a noble but elusive pursuit. Similarly to how energy can be taken from splitting heavy atoms, like uranium, light atoms like hydrogen and its isotopes can be fused together to achieve the same thing, which, for example, is what stars do, but you may notice the sun doesn't really match the conditions we have on Earth. In our case, we have to build very specific reactors to contain very extreme conditions. A long-studied way of doing this is the tokamak, a donut-shaped chamber with magnetic coils holds hectomillion-degree plasma suspended in air, requiring our best understanding of how plasma behaves when exposed to magnets. But our knowledge is incomplete and there is room for surprises in the experiments. One such surprise that occurred in the 80s was the H-mode, a sudden transition leading to far greater confinement, meaning higher temperatures and pressure, and thus closer to the goal of fusion reactors. The plasma's edge suddenly became far more impenetrable, acting as a wall, and so that made it hard for plasma to diffuse. This region is called the pedestal due to its steep appearance in plots. However, if it becomes too steep, it may trigger an instability called an L, which can send plasma into walls. So we have this promising regime, but it sometimes becomes angry and throws glowing hot things at our very expensive walls. Under very specific conditions we have found, it is possible for the mode to relax, and we call this the EDA H mode. It's an H mode that learned how to do meditation. Much like a breathing exercise, we suspect the EDA remains chill, by never letting its pedestal grow too steep, likely thanks to the action of a perturbation called the QCM. This benign instability is always present in EDA-H modes, and so we study it to ascertain whether the EDA will be possible in future reactors. Current reactors are big, but future ones like ITER and DEMO will be truly gargantuan beasts, and with different properties. One such property is the collisionality. How often particles bump against each other, and it will overall be lower. However, the QCM has only been observed at high collisionalities. This is where the location of the QCM gains significance. You see, the collisionality decreases along the pedestal. This makes it so that the QCM will only be able to form at the bottom of the pedestal of future tokamaks, despite the fact that it may show up anywhere in the pedestal region of current tokamaks. We aren't sure of its location as current measurements are inconclusive. We need more measurements to extrapolate into the future with more certainty, and that will be the starting goal of my thesis.
Teste. Vai funcionar? Hello everyone. That was the peak of the presentation. Now we'll come down a little bit and talk a bit how I'll actually be doing this measurement, which is through reflectometry, which is a type of diagnostic that's been talked about before in one of these presentations, and that is at its core, it's relatively simple. We're just sending waves into electromagnetic waves into the plasma, and that reflected at some critical density layer. And so we need to know, have a succinct model for where this occurs. I'm doing this backwards. But essentially what we can do when we have that is if we rapidly vary our probing frequency for our detector, we can probe the various densities of our plasma. However, this isn't a radial measurement just yet. This is what was done previously last year by a thesis of a colleague of ours. But what he obtained was an intermediate result. This is the amplitude in terms of the phase, and this is just the probing frequency, but these need to be turned into real physical units to be interpretable and be published in a scientific paper. One of the difficulties with this is, for example, in the last slide we had the y-axis, which needs to be transformed into a physical result, and one of the difficulties with this is, for example, for the same phase variation, which is this x-axis here, depending on what our local density gradient is for that layer of the plasma, we get a radically different physical result. So things that seem similar in that graph are actually quite different. I will be doing these measurements using data from the HDEX upgrade, which has a reflectometer system operated by IPFTN. Yes, that is all. Thank you.
Okay, great presentation again. There's any questions?
I don't have a question. I just want to say that your video was really good.
Thank you. Great. So I have a question. And what are the advantages of the reflectometry?
So one of the main things is just that reflectometry can be done from a safe distance, as in, if you're actually using a probe that touches the plasma, it's touching a very hot thing, it might melt, it will suffer damage. Meanwhile, reflectometry you can do from a distance. But it's also that it's quite resistant to essentially misalignments. Because what we're actually measuring isn't a radial position, it doesn't matter if our reflectometer is slightly misaligned, because it will always, depending on our probing frequency, will always reflect at the same layer. And so if we then complement that with other measurements, it is consistent in that sense. It is more robust.
Okay. Do we have time for another question? Yeah. So how can you measure the density profile?
The strength of this method is that, okay, we're measuring something that still needs to be complemented to actually gain a physical result, but any method, there are many measurement methods in plasma physics, any of them can plug into this and give us what we need to actually obtain a physical result. And one of the ways is actually just another type of reflectometry. So what I'm going to mainly be using is hopping reflectometry, but there is another type that can be used to essentially measure the density profile and can be plugged into this. So with two types of reflectometry, we can achieve this goal of attaining a physical result, which will be my goal.
Okay, perfect. Thank you.
Thank you.
Okay, so now I will introduce you to David, which is very interested in high energy neutrinos, and he will develop simulations to evaluate particle showers and combine these simulations to develop data analysis in the PIC2 Observatory. Okay.
From it. I am working at LEAP on the improvement of neutrino detection at the PIC2 Observatory.
First of all, neutrinos are almost massless particles with no charge, which very rarely interact. For these reasons, when emitted from an astrophysical source, they easily escape it and travel in a straight line without deflection or absorption, so they can be used to determine the source's direction. This is particularly relevant in the context of multi-messenger astronomy, which is a technique which combines different messengers from one event to obtain more information about it. The most common of these messengers are charged particles, such as protons or ions, which are known as cosmic rays. Their spectrum is composed of a few features, but overall, the flux decreases with energy up until a cutoff predicted by the GZK effect. The most extreme sources can produce cosmic rays in the ultra-high energy region, which, for the case of protons, can lead to the creation of ultra-high energy neutrinos, but so far none have been detected. When reaching the Earth, these highly energetic particles interact with the atmosphere and form a shower, or cascade, which typically has three components. The hadronic component is closely tied to the muonic one, so you can use the muonic signal, S-mu, to infer information on the hadronic cascade, which, due to the extremely high multiplicities per interaction at these energies, will most likely not reach the ground. At the same time, an electromagnetic cascade competes with its hadronic variant, and its signal upon reaching the ground observation level is known as SAM. These cascades typically present Gaussian-like longitudinal profiles, and the depth at which the maximum number of particles is present is called Xmax. PIC2 Observatory in Argentina was built to detect ultra-high energy cosmic rays, but has conducted searches for ultra-high energy neutrinos using techniques like Earth-skimming neutrino detection, where the event's direction can only be compatible with a particle which interacts as little as a neutrino does. This technique is very effective, but severely limits the observatory's acceptance because it only covers a very small band of the sky. Recently, PIC2's detectors were upgraded with scintillators and radio antennas, enabling detailed measurement of shower development features. This upgrade opens new possibilities for directly measuring and distinguishing SAM and S-mu. To solve the coverage problem, these signals can be used during the analysis of vertical events to distinguish between neutrino and proton-induced showers, since their depth of first interaction can be very different due to the low interaction probability of the neutrinos. To separate the two simulated populations, a Fisher linear discriminant analysis can be performed to extract the array's neutrino detection efficiency for any given background rejection factor. Since no neutrinos have been found, we can then use this efficiency to impose upper limits on the differential neutrino flux. The results I've obtained so far, despite not being amazing, seem to indicate that this is worth researching, since vertical neutrino event detection would boost our sky coverage to its maximum. To improve this detection efficiency, my master's thesis will focus on using Xmax information to further increase the distinction between proton and neutrino events. To accomplish this, I first started by fitting my simulated events to a Geiser-Hilles function. Afterwards, I split my events in Xmax bins and performed the same Fisher-Cut analysis as before. In some Xmax bins, the distinction between signal and background visibly increases. However, the Fisher-Cut encountered some inconsistencies due to the low statistics per bin. To resolve this issue, I will switch my approach to a boosted decision tree analysis. I will also explore the possibility of extracting the longitudinal profile from the radio antennas installed during the upgrade.
Thank you for your attention. Hello everyone, my name is David Diaz and I'd like to summarize a little bit my master thesis project on improving neutrino detection at the PIC2 Observatory. Okay. So first of all, what are neutrinos? Neutrinos are almost massless particles which have no charge and very rarely interact, which I find very relatable. They make for excellent astrophysical messengers since they can easily escape their astrophysical sources and they travel in a straight line without being deflected or absorbed. Multi-messenger astronomy is just a technique which combines different types of information carriers, as you've seen in the video, and uses them to find out more information about any event. Neutrinos are particularly useful since they can pinpoint the exact direction of a source. Okay. So when a highly energetic particle reaches the Earth, it forms what is called an extensive shower or a cascade, which is, you can see in the image, it typically has three main components, which is hadronic component, muonic, and electromagnetic. When reaching the ground, you can measure a muonic signal to infer information about the hadronic cascade, and similarly, you can measure the electromagnetic signal, SAM, to infer information about the electromagnetic cascade. Another important parameter to keep in mind about these cascades is known as Xmax, which is just the depth at which the cascade reaches its maximum number of particles. PIC2 Observatory, located in Argentina, was built to detect ultra-high energy cosmic rays, which are another type of messenger, but has adapted a technique called Earth-skimming neutrino detection to search for neutrinos. This technique is very effective, but severely limits sky coverage. So, due to recent upgrades to PIC2 with new scintillators and radio antenna upgrade, it is now possible to perfectly distinguish the electromagnetic signal SAM and the muonic signal SMU, and we can now use this to find more information about vertical events and then potentially solve this coverage issue. Okay, so how this is done is very simple. Like I explained before in the video, you just do a Fisher-Cut, which is just a linear analysis, and the points of neutrinos which make this cut are counted, and then we obtain an efficiency, which is just the total number of points in comparison to these points which make the cut. And since no ultra-high energy neutrinos have ever been observed, we can oppose upper limits on the differential neutrino flux using this formula. Okay. So, previous results I've obtained from working on this topic have already suggested that, yes, this is a viable strategy, and we can, in fact, detect vertical neutrinos events. And my master's thesis will just focus on using information which is Xmax to complement SAM and SMU by feeding longitudinal profiles, extracting the parameters, and basically splitting the Fisher analysis in Xmax bins. I've realized that there's a little statistics problem to this, so I will switch my analysis to a method called boosted decision tree, which you might know. I'll also explore the new radio antennas being installed to solve the low duty cycle of the fluorescence detectors, which are used to obtain the longitudinal profile used to extract Xmax. I hope with this project I can increase the detection efficiency and open up the maximum potential of the observatory's coverage. Thank you.
Thank you very much for the presentation. There's any question?
Okay. I'm sorry, I didn't quite understand why can we only have like a strip of the sky?
Yeah. So basically, the most effective strategy you can have is the Earth skimming neutrino method. Why? Because basically neutrinos interact very little. So if you only look for particles coming from basically the ground direction, you know that the only thing that can come from this direction is a neutrino, because if it was like a cosmic ray, a proton, or something else, it would bump into the ground and create its cascade much before reaching the detector.
Thank you. Okay, there's a question there.
Hi, so I just wanted to ask you, why didn't you use, before the decision, the quadratic discriminant analysis? I don't know if it was useful or not.
We just didn't explore that option. I started by using a Fisher analysis because, well, the data seemed very simple, easy to cut, but as I explored splitting into different bins, I realized that it was not so simple, and it wouldn't really match any linear or quadratic or anything remotely that you could extract any significance, physical significance from it. So we decided to skip directly to machine learning and use BDTs.
There's any more questions? Okay, so it's all. Thank you.
Thank you.
So now I would like to introduce you to a dear friend, a person that knows some things. So Bernardo Picão will explain the basics of lattice QCD and how these theoretical calculations can help guide future experiments.
Those little fellas are electrons. They are very light and swirl rapidly around the nucleus. A nucleus is made of many neutrons and protons. But what are they made of? Let's find out. Those are quarks. They come in 6 different flavors: up, down, strange, charm, bottom, and top. As you can see, some are much more massive than others. There are 3 inside a proton, 2 up and 1 down. Quarks interact by trading back and forth particles called gluons. This exchange creates a springy tube between them called a flux tube, which binds them together very strongly. If we try to pull them apart, the tube stretches and stretches until it snaps, and 2 new quarks are created in between the old ones. This means that quarks can never be alone by themselves. They can hang out in pairs, in trios, or sometimes in 4s. These 4-quark systems are called tetraquarks. We don't know much about them since they are very rare and hard to observe. However, we can use powerful computers to calculate how they behave. Here's how we do it. First, we pretend that space has a finite resolution, so that the quarks all sit on a grid and the gluons run along the edges. Then, for our tetraquark, we pick 2 really heavy quarks, bottom quarks in this case, so that, during the time of interest, they barely move and we don't have to actually simulate them. The 2 other ones are lighter U, D, or S quarks and hang around the first. The computer will then tell us how the system evolves. We can use it to predict the real-life measurement of the energies of these particles. These theoretical results can be compared to experimental observations from particle collisions, thus helping confirm the detection of these exotic particles. With these tools and a little curiosity, we are ever closer to unraveling the secrets of the universe. Thanks for watching.
It's fine, you can hear me properly, right? Yeah. I'll just...
Closer to the camera.
Yeah, I can speak from here. Yeah. There we go. Okay. Hi everyone. So today I'll be talking about my project of lattice tetraquark spectroscopy and disentanglement of ecstatic states. So this work is funded by SFEMA and in collaboration with Goethe Universität in Frankfurt and the ETH in Zurich. So ever since the 60s, physicists have predicted theoretically the existence of what's called exotic QCD matter. So this is either hadrons that have more than 3 quarks, so either 4 tetra, penta, hexaquarks, etc., or else also glupols, which are bound states of gluons, or even hybrid hadrons, which contain gluons and quarks. And since 2003, the Bell collaboration discovered this first tetraquark candidate, the X3872, and then a slew of other resonances were discovered that can be summarized in this map. This is just for the charmonium spectrum, so exotic matter that contains charm quarks. And this sparked a new interest into this area of research in particle physics. And one of the strategies to attack, to understand more better these particles is through lattice QCD. So the idea is that we discretize the space-time continuum into a 4-dimensional lattice, and we place the quarks, the fermionic degrees of freedom, in the vertices, and then the gluons live on the edges. And from this, then we can compute observables and extract physical predictions from these lattice calculations. Unfortunately, these calculations are extremely computationally intensive. So this is the cluster that I used to do the calculations. It's the Goethe cluster in Frankfurt, and even with 4,100 CPUs working in parallel, this still takes around 20 hours, upwards of 20 hours to do a single lattice calculation, so millions of computer hours. And the code that I've used in my thesis was inherited from a PhD student from the consortium, and I am trying to expand it and clean up some of the results that he obtained. So basically the idea is to disentangle the contributions from excited states that overlap with the ground state that we want to observe of our tetraquark, and from there extract better values for the potentials and the energies. And this code involves treating huge amounts of data and upwards of 20,000 files, so a lot of statistical modeling is required to extract physical predictions. And this is some of the results that we get. So this is the potentials inside the tetraquark system. And you can see that they are discriminated in terms of their quantum numbers. And just as a visual example of some of the calculations that we did. So thank you for watching. So if you have any questions, feel free. About the video as well, if you want.
Yes. Okay, please. Yeah, I know that time is not enough for everything, so could you expand a bit more on the results that you got? I didn't quite get the importance of it.
Yeah, thank you. So these results are still from Lasse's PhD thesis. I don't have entirely new results yet.
But these potentials are for systems of tetraquark systems that have two heavy B quarks that we can consider as static, like in the video you saw. And this is the potential basically between the B quarks, the static quarks. And then the other two light quarks are considered as dynamical. So he did a bunch of graphics for U, D, and S dynamical quarks. And with these theoretical predictions, the idea is that we can guide then observational discovery of resonances for these systems, tetraquark systems, which are still haven't been discovered for B tetraquarks, basically.
Okay, I think that there was another question there. Okay.
So you mentioned that when doing lattice QCD, there is a discretization of space involved.
Yeah.
In this
Space-time.
case,
Space-time. Yes.
Yeah, space-time. So regarding the spatial time, I'm sure you can do that. Do you have an idea of the spacing between each vertex?
Yeah.
In this case, the study of time.
Yeah, so I mean, I didn't go into any sort of detail into how you actually do that, but yeah, so the lattice is four-dimensional. It is usually a little larger in the time direction than the three spatial ones. And obviously it has a lattice spacing, right? And that lattice spacing is then, basically what we do is we compute the observables at a few lattice spacings for a certain configuration and a certain ensemble of configurations. And then we take that lattice spacing, we extrapolate the result to zero lattice spacing, which would be the continuum result, right? And I mean, there's a lot of subtleties in how you do that, either theoretically, whether that works at all, that's it, you know, it was non-trivial result, and also how to actually pragmatically do it. So in my report, you have some examples of that sort of extrapolation, but it's definitely something non-trivial. And also, how do you fix that scale with respect to real life, right? So that has to do with the pion mass, or like you can compute observables that are well known, make sure that you have the right results, and then try to compute the hard stuff.
Okay, so there was one more question, right?
Quick question: how long did it take to do the stop motion?
Yeah, so I don't know. It was a fun idea. It took me like about 4 days of working the whole day through the night as well. It's more than 1,200 images in the video, but I think the result was quite fun. Thank you.
Okay, so I think it's okay, and we are going to close this section and wait for the next. Okay, we start again at 4. Okay, sorry.
So hello everyone, I want to give you a warm welcome to the last block of presentations that we will have today. So my first speaker will be Gonçalo Barreto, that will talk about multi-Higgs doublet models and softly broken symmetries, as well as he's going to understand further particle physics.
Hello, my name is Gonçalo Barreto and I'm a master's student at Instituto Superior Técnico under the supervision of Professor Yves Varzialas. My thesis is in the area of particle physics. In this area, the most successful theory is the Standard Model. This theory describes all known matter particles, which are fermions, and have all the forces and interactions between these particles. These interactions are carried by vector bosons, and the remaining particle left is the Higgs boson, which is a scalar. The Higgs boson was discovered in 2012 at the Large Hadron Collider and is responsible to give particles their masses via the Higgs mechanism. The Large Hadron Collider, or LHC, is the most complex set of experiments performed by mankind. It is located in Geneva, and the experiments that found the Higgs boson were ATLAS and CMS. Although the Standard Model is incredibly successful, but it still has its flaws. The main phenomena that the Standard Model cannot explain are gravity, neutrino masses and oscillation, and dark matter. These open questions motivate beyond the Standard Model physics. This topic is the main research area in particle physics. There are many famous ideas, for example, supersymmetry, but recently researchers have been shifting their attention to different and perhaps more interesting ideas. In the Standard Model, one can add more Higgs-like particles, and the model still remains consistent. This type of models are known as multi-Higgs doublet models. In multi-Higgs doublet models, one can add generational symmetries to restrain and simplify the theory. The way that the symmetry is implemented is by forcing the Lagrangian, which is the fundamental quantity, to be invariant under all actions of the symmetry group. Symmetries have a crucial role in all areas of physics. They let us simplify and understand problems in a more profound way. My thesis consists of building a 3 Higgs doublet model and apply the sigma 36 symmetry group. Next, I choose a specific VEV and turn on the soft breaking parameter that does not preserve the VEV alignment. With this new VEV, I can calculate the mass matrix and the corresponding masses of the physical scalars. These models are interesting because they can create domain walls, which can be sources of gravitational waves. Gravitational waves have been detected at LIGO in 2015, and the gravitational waves created by domain walls may be detected by LIGO or by other future detectors that are being built today. Hello everyone, my name is Gonçalo, and in my pitch I will give some further details that I wasn't able to do in the video. Okay. Okay. So, as I said before, symmetries play a fundamental role in all areas of physics. To understand symmetries, we'll need group theory. A group is a set of elements that has closure, associativity, identity, and inverse. And here we can see all the discrete groups that can be applied to a 3 Higgs doublet model. So the biggest one is that sigma 36, and that's why I choose that one to work with. In this group, it is equivalent to Z3 cross Z3 cross Z4, and here this is the generator of the first Z3, this is the generator of the second, and this is the generator of the Z4 in this specific representation. So, as I said before, we have to make sure that the potential is invariant under all actions of the group. So we only need to make sure that it is invariant under the actions of the generators. And here is the potential. So we can use geometric minimization to have the VEVs, which are here. And in this potential, the VEVs are degenerate. But by adding soft breaking parameters, which are quadratic terms that are not invariant under the generators of the groups, this degeneracy, so these graphs are no longer degenerate. And by quantum tunneling, the graph can go from here to here. And by this, it releases energy, and this energy is released by quantum gravitational waves. So in this paper that I will be making, we'll choose a specific path, activate one soft breaking parameter, and minimize the potential. Have the mass matrix and the masses of the physical scalar, and check if there are decays into non-standard model Higgses. So this project will also aim to give an introduction to research in particle physics. Thank you very much.
Does anyone have questions?
Yeah, so thank you for the presentation. I was wondering, so the Z4 semi-direct model for the signature, so that acts by conjugation on the potential. Is that what you do?
Yeah, exactly.
Any other questions? No? So I have one. So you talked about generational symmetries, correct?
Yeah, exactly.
So are there any other types of symmetries that you can force Lagrange into being invariant?
Okay, so yeah, we can do space-time symmetries, for example, CP or T transformations, and this Lagrangian in particular is invariant under CP, the CP transformation. So it will not, the Higgs sector of this Lagrangian will not contribute to CP violation, and so the baryon asymmetry will also not, so there is the baryon asymmetry problem, and the Higgs sector will not explain this. But the Yukawa sector given by this 3 Higgs doublet model can explain that CP violation.
Okay. And so are there any restrictions that you need to impose for the creation of the domain walls?
Yes. So here we can see that the domain walls are created by quantum tunneling. And we have to make this half-life to be equal to the life of the universe so that the gravitational waves are created now.
Okay. I think it's... So give him a round of applause. So, next, I have one more speaker, that is Gonçalo Ribeiro, and he has been working on addressing one of the main limitations of the
Please welcome Bruno Lima.
Space and its secrets have been the source of many questions for centuries. To answer them, one must leave the comfort of the Earth and face, among many threats, an invisible and particularly hazardous one: radiation. Understanding space radiation is critical for the future of space exploration, and the first destination is the Moon. But how can our neighbor be so close to us and be so drastically different? Unlike Earth, the Moon has no protective magnetic field or atmosphere. It's constantly bombarded by high-energy particles from space called cosmic rays, and occasionally by particles coming from the Sun called solar energetic particles, among other sources. Galactic cosmic rays, also known as GCRs, come from outside our solar system, created by distant supernovae. They are incredibly fast-moving at nearly the speed of light. Their particles can travel across the universe for millions of years before colliding with the Moon or an astronaut's body. Then there are solar energetic particles, also known as SEPs. Unlike GCRs, SEPs are unpredictable. They are associated with violent explosions on the Sun, solar flares, and coronal mass ejections. This can send deadly waves of radiation towards the Moon in just minutes. Astronauts caught outside without an efficient protection during one of these storms could receive a radiation dose equivalent of hundreds of chest X-rays in just a few hours. But what does this radiation actually do? Well, at high doses, it can damage human DNA, increasing cancer risk, which, for long-term missions, is a serious concern. But it's not just humans. Radiation can also affect spacecraft electronics, corrupt data, and even weaken materials used in spacesuits and spacecrafts. I'm developing a new lunar radiation model called the LERAM, that stands for Detailed Lunar Energetic Radiation Environment Model, based on an existing Mars model, the MERAM. Using powerful computer simulations with GM4, the goal is to be able to track how radiation behaves on the Moon. This will help scientists plan safer missions, design adapted spacecraft shielding, and even assess health risks for astronauts. This research isn't just theoretical and has foreseeable applications. ESA projects such as the Lunar Gateway, the Orion spacecraft with the European Service Model, and the Heracles lunar lander, among others, can take advantage of this model. By using programs like the LERAM, we can study the safest landing sites, plan habitats, and reduce radiation exposure risks. Space exploration is entering a new era. The Moon is the next step, but radiation remains one of the biggest challenges to overcome. With models like this, we are equipping scientists and engineers to plan safer missions, protect astronauts, and pave the way for long-term space exploration. One day, humans will live and work on the Moon, maybe even travel to Mars. And the work we do today, understanding radiation, designing better shielding, and predicting risks, will make that future possible. My master's dissertation thesis. Sorry. Can you go back to the first slide? Okay, thank you. Entitled The Lunar Ionizing Radiation Environment, a Benchmark Model. First and foremost, why do particle physicists matter to space exploration? So, if there is one thing that particle physicists are very good at, among other things, is a simulation of interaction between particles. And if we want to go to the Moon, where we have a very relevant radiation environment, this is a need. Thank you. So, as you've seen in the video, there are several sources of radiation environment on the Moon. The main ones are GCRs and SEPs due to their energy and flux values, which essentially make them the biggest contributors to the radiation environment, as I said in the video, and they're the main ones that I'm going to study in this model. Okay, so how do I propose to do this? So I'm going to build on a model that has already been developed by my research group, SpaceCloud, for Mars. And so how does one actually develop this to the moon? So we need to, of course, replace the Mars-specific data, such as the atmosphere or the soil models. The moon does not have atmosphere, so it's an entire different backbone entirely. We need to include learner-specific radiation sources. Of course, GCRs and CEPs are global to radiation environment in space, but their values are different, so there's a need for a new database. And lastly, the main goal of this is to validate this project with actual research data. And so I call your attention to this task, to the first and the last task, which is the validation of data. I really call your attention to this. This is really important because, as you can imagine, accessing data that is from ESA, NASA, etc., is a very hard step. But it's a very important one because it's the only way that we can assess that the model actually works. And so here I present to you a very simple, very simplistic model of radiation environment. I have here a simulation of lunar regolith, and it's simulated with a flux of 100 gigaelectron volts. And what do we see? We see that we can actually use this model to predict how particles interact, their path, and the production of secondary particles, which is a very important point. Thank you. And of course, Delirium, it has many, many purposes and many objectives. Of course, my main goal is scientific research, and I call once again your attention to the validation approach. This model, it's going to help human spaceflight safety, lunar mission planning, of course, but this only matters if we are actually able to compare it with data that we have from the in situ measurements. And so, in conclusion, very summarily of my project, the goal here is to provide a benchmark. So we have a model that all scientific research community can use to have the simulation of radiation environment, so that when astronauts go from Germany training center to actually the moon, we can make sure that they are safe. Thank you for your attention, and I'm open to questions.
So we will now. Okay, nice, awesome. One question already.
Thank you for the presentation. So I was wondering, is there a big difference between doing a test like this, so sending a small sample of lunar regolith to like high Earth orbit and seeing how it stops radiation versus actually being on the moon? So since the atmosphere doesn't really work.
Yeah, so it is very important, and actually there's this thing that the moon actually does have a very thin atmosphere, but we don't consider it because it does not have measurable attenuation of radiation. So we don't consider it in the models. It is very important because I have them here. Yeah, so in the other sources, and there are albedo particles, which are the particles that come from the interaction of GCRs and CEPs that are very relevant. For example, neutrons, because neutrons are very hard to stop. And for example, they are very relevant to the radiation environment. So yeah, it's very different. Yeah, thank you for your question.
Okay, do we have any more questions? No? I have one for you, Bruno. Well, what are the major difficulties associated to this sort of project?
Yeah, so thank you for your question. And of course, there's obviously a computational problem here. This is a very difficult challenge. If you'd see the code, you probably stress out. But essentially, the main constraints here are exactly the data. So, with comparison to other experiments, I cannot go to the moon and make the measurements of radiation, right? So I have to depend on big experiments such as NASA, ESA, and many others that have this data and expect them to provide it. And News Alert, normally this is very difficult data to access to. So this is a very difficult and important constraint. Thank you.
Yeah, do we have questions?
Can I just underline one of the points that you said, and I would like to elaborate on that? Because actually radiation protection of our astronauts is really hard, and people are investing in space exploration. So what are your thoughts in that matter? People are, like Elon Musk, are always claiming that we are going to Mars soon. That poses some issues that you are trying to solve, right?
Yes, and that's a very interesting point, because actually one might think, all right, this is a big challenge, and of course if we want to go to these places, and for example, for you to get an idea, a mission to Mars has a timeline of about 2 years because we cannot just simply go and go back because of the position of the planets, of course. And so 2 years outside of Earth's magnetosphere and atmosphere, it's a lot of radiation to take into account. But actually what happens is that there are not many studies on this and many things being made of this. So yeah, this is a very important topic. Yeah, thank you.
Okay, thank you for your questions.
Thank you.
Thank you, Bruna. The next speaker has spent years upgrading his skills on programming and computer science, and today, on our Discord servers, by the way, guys, and today he's going to show us the work he's doing on Atlas calorimeter algorithms calibration. Yeah? Please welcome Bruno Smiel.
There is a general purpose detector at the highest energy collider in the world, the Large Hadron Collider, or LHC. It aims to identify the fundamental blocks that compose our cosmos and the origin of the universe itself. It processes a whopping 60 terabytes of data every second. And where does all this data come from? Well, there is something called a bunch crossing every 25 nanoseconds. That's millions of times faster than the blink of an eye. A bunch crossing occurs when a collection of protons collides with another, producing around 50 to 60 proton-proton collisions each time. This is already a lot, but in 2030 the LHC will undergo the high luminosity upgrade, increasing this number even further to 200. This is crucial for studying rare phenomena and hunting for signs of new physics. But how can we store so much data while running this experiment for years? Well, we can't. We need to choose which events we want to store, like snapshots of the interesting collisions. The trigger system filters the 40 million collisions per second to fewer than 3,000. First, with a hardware trigger, and second, with a software trigger, which is where my work fits in. Let's discover a bit more. The high luminosity upgrade poses a challenge. Our current computing infrastructure cannot handle the increased data volume, and this is where GPUs come in with their massively parallel architecture, being able to perform thousands of computations at the same time. What exactly am I doing? I'm working with one of the algorithms in the trigger, passing it to GPUs and optimizing it as much as possible. But before I can tell you what this algorithm is, we need to take a brief look into calorimeters and the standard model. Part of the Atlas detector is composed of calorimeters. They're made of dense materials to stop the particles from escaping so that we can measure their total energy. And they are divided into more than 180,000 cells to tell us where they deposited their energy. Imagine a camera but on a bigger scale. When we take a photo, each pixel records what it was seeing and where it was in the image. This is the standard model of particle physics. Our universe is governed by 4 forces, but let's focus on 2. The strong force affects the particles called quarks, and the electromagnetic force, which allows us to lead our everyday activities like walking or charging our phones. The family of leptons also shows a familiar friend, the electron, and the elusive neutrino, which almost never interacts. Now I can tell you about the algorithm I'm working on. In the calorimeter, neighboring cells with energy deposits are first merged into clusters. These clusters are then calibrated to ensure precise measurements, which is my focus. There are 3 main effects we need to correct for, but first we need to classify these clusters into electromagnetic or hadronic. They are electromagnetic if they come from particles like electrons or photons, or hadronic if they come from hadrons, which is 2 or more quarks held together by the strong force. Think of it like a molecule but for subatomic particles. This is important since we will apply different calibrations in each case. We start with the hadronic calibration. When hadrons interact with our calorimeter, we can't measure all their energy, like with their electromagnetic counterparts. They can lose energy via the strong force, which we cannot detect, and also produce neutrinos, which will just escape the detector never to be seen again. When the clusters are being created, some cells never get invited into the party and are just left outside of any cluster. Even though these cells were outcast by the cluster society, they may also contain important signal for our event, which needs to be accounted for. Finally, there is the dead material correction, and no, it has nothing to do with CSI or police investigations. In the middle of the calorimeter there is inactive material, where particles also leave their energy but we cannot measure it. This happens because the calorimeter modules also need physical support, as well as data acquisition systems. By parallelizing these algorithms using GPUs, we were able to obtain some preliminary results offering speedups of 22 times compared to using an ordinary CPU. Not everything works perfectly yet, but that is science, a process of continuous refinements, and every challenge brings us closer to unraveling the secrets of the universe.
Everything set up? Thanks. So, as we just, it doesn't move, perfect. So, as we just saw, there is a large amount of data that we have to deal with. 60 terabytes of data every single second. And with a high luminosity upgrade coming in 2030, we will have even more data, which we simply cannot handle with our current infrastructure. And GPUs offer a great solution for this with their massively parallel architecture. And how am I helping to solve this problem? My goals are to port the colorimeter calibration algorithms to GPUs and optimize them as much as possible. And this is especially important since we need to influence the decision of using CPUs or GPUs during the next upgrade, and of course, well, use them in case they are chosen in the trigger system. These are the 4 algorithms that we took a look at in the video, and the calibrations are absolutely essential since we need to reconstruct physics objects accurately, so we need correct measurements of their energy. And then, how are they done? First, we need to, some calibration coefficients are obtained using Monte Carlo simulations, and they are stored in a database. And then, my algorithms are run on the fly using this, and access this database to use these calibration coefficients. And so, a very simplified process of this is how do we use them? We basically start with some clusters and some cells, we put it through some filter, and then the ones that survive, we need to, based on their properties, get some coefficients from the database. Do some computations with this, and finally, we go to each of the cells from these clusters, and we apply the coefficient corresponding to that cell. And finally, recalculate all the kinematics for that cluster. For example, what's the center of gravity? Then, this work is one of the ones that's pioneering the GPU era of Atlas. Out of 52,000 files, only 28 of them are now made for GPU. And what are GPUs? Well, they are massively parallel since they have thousands of small cores. We can see here one of the building blocks of a GPU, which is composed of 4 warps, each of them having 32 threads. And we basically program what each of these threads is doing, which is a completely different programming model and a completely different mindset to be able to program it compared to a normal CPU. Regarding some preliminary results, starting off with our classification algorithm, everything agrees with CPU. We can see here the absolute error, and here the fraction of clusters. We did just see an amazing peak at zero absolute error. So amazing. And now let's look at the others. So for hadronic calibration, by the way, please don't be scared by the log scale. Here we don't get an exact match. 63% of our clusters exactly match with CPU, and 87% of them differ less than 10%. And we have similar results for the remaining tools, which were tested independently. Regarding speedups, we got an average speedup of 11 times for jets and 22 times for TT bar, with tails even going up to the 120 speedup. But then you can ask, aren't the results wrong? Why are we even talking about execution times? Well, we checked that they are performing approximately the same number of operations as the same number of clusters are passing each cut, so this is a valid approximate measure for the speedup which we will get. To conclude, we are currently porting 4 calibration tools to GPU, getting a speedup of 11 times for jets and 22 times for TT bar, with 87% of these calibrations having less than a 10% difference, which is a very good setup for future work. And in the future, it's very important to understand better these differences so that you can get a 100% match or close to it and get even more optimized algorithms. Thank you. Shoot me, preferably with questions.
We have, let's start. Oh my god, let's start here. I think it was the first one to raise the arm.
Go ahead.
So, as someone who also is Google for a bit, I know it's an absolute pain. I was just wondering.
It's beautiful.
Yeah, I was just wondering if did you micromanage the RAM like separately? Did you play with different types of cores, like I know NVIDIA graphics,
like tensor cores and whatnot?
Stuff like that.
This, in this case, for example, using those types of cores doesn't make much sense. Tensor cores are very useful when we do a bunch of matrix multiplications or vector multiplications. But in this case, the algorithms themselves are very serial. They need to be ran serially. So we are parallelizing across the clusters or the cells, depending on what we're doing. But we cannot really do that since there's no way to join them in the matrix somehow. At least not that we've thought of.
Okay, next question. Console?
Yeah.
Okay, just probably a dumb question.
Go ahead.
You said earlier that they are still deciding whether to use CPUs or GPUs. So what I saw the results, pretty remarkable, by the way.
Thanks.
Why they haven't decided yet?
Well, it's planned to be decided at the end of 2026. We are currently still during run 3, which will end this year, and run 4 only starts in 2030. For now, we are just developing options, let's say. And after that, there still needs to be analysis because we need to have confirmation that it's possible to port all of this. You saw 52,000 files. We need to be able to, we need a lot of manpower to be able to port all of these algorithms that are required to be able to run in 2030. And this is a lot. And first we need some proof of concept that it's doable. So this is part of that proof of concept.
Okay, thank you.
Thanks.
For our last question, your person, please. No?
Okay, no need, thanks.
Okay, excellent. Yeah, I guess I can shoot you here a question.
Okay.
I have here. So, you said that, I just don't know where, but there was a plot of speedups,
Yes.
and there's a major speedup for TT bar events.
Yes.
Rather than jets. Can you explain a little more about that?
Yes, let me just find the backup slide that I want, which is at this one. So, jet events, as we can see on this Feynman diagram, usually, this is usual, not all of them are the same, but usually jet events produce about 2 jets, while TT bar events produce at least 4. And since we have this architecture, we basically, summing up everything is just, we have more computations, we have a more beneficial use of GPU. But if you want to think about it a bit more deeply, then we need to look at the complexity of our algorithm is basically linear. So what that means is our time of execution of the algorithm scales linearly with the amount of things we need to process. And it's basically linear on CPU. But since we have thousands of cores, and the number of clusters is also on the thousands, on the GPU, the complexity is basically either constant or just logarithmic. So it scales a lot better, and for TT bar, it will make a lot more difference since we have a lot more things to process.
Okay. Thank you, Bruno.
Thanks.
Lovely presentation.
Thank you.
Okay, our next speaker is going to talk about a topic that I literally don't know nothing about, which is PET scanners. So I'm really excited for this one. Please welcome Marta Simões.
Cancer is a group of over 100 diseases caused by uncontrolled growth of cells, leading to malignant tumors that invade surrounding tissues. In 2022, the World Health Organization reported 20 million new cancer cases and 9.7 million cancer-related deaths globally, a stark reminder of a urgent need for better treatments. Hello, my name is Marta Simões and I am an MF student. Today, I will present my project, which focuses on optimizing the design of a flat panel PET scanner with depth of interaction capability. Proton therapy is a cutting-edge cancer treatment that precisely targets tumors while minimizing damage to healthy tissues. However, its success relies on accurate verification of the proton range. Uncertainties in this range can result in underdosing tumors or overdosing in healthy tissues. Positron emission tomography plays a crucial role here, enabling verification by detecting pairs of 511 kV gamma rays emitted during the decay of highest adoption rated in proton tissue interactions. PET scanners will rely on high-density scintillation crystals, like LISO, paired with silicon photomultipliers, to produce detailed image. PET spatial resolution is influenced by the positron range, the clarity of the gamma pairs, and the PET detector width. However, without accurate depth of interaction capability, parallaxal errors occur. This happens because the system assumes that photon interaction happen at a fixed depth within the crystal, even though actual interactions vary by depth. These errors lead to radial artifacts and reduction in image quality, especially in the area of the field of view. My project aims to address this challenge and advance PET scanner technology through 3 key objectives. Develop a Monte Carlo simulation model for the scanner's detection unit, consisting of a scintillator and 2 silicon photomultiplier sensors. Improve depth of interaction resolution by testing different crystal size and encapsulation techniques. And finally, characterize the scanner's performance across the entire field of view to minimize distortions. To achieve these goals, I am using Hands3, a software interface for the Gen 4 toolkit, to perform Monte Carlo simulations. This approach allows precise modeling of the system geometry, material properties, and optical behavior. Important factors like surface roughness and light refraction mechanisms are incorporated in the simulation to enhance its accuracy. The model will be validated using experimental data previously collected at the University of Texas at Austin, ensuring its reliability and predictive power. Once validated, the scanner design will be refined to optimize spatial resolution and minimize image distortions. These improvements will culminate in a more efficient PET scanner capable of delivering high-quality image and greater detection accuracy.
So hi, I'm Marta, and I will talk my project. So cancer is this huge group of diseases where a complete cure remains a challenge. So proton beam as proton therapy is a cutting-edge cancer treatment that precisely targets tumors while minimizing the damage to healthy tissues. Prompt gamma and positron emission tomography are the most promising techniques for range verification, but as PET can provide 3D image is the preferred option. So when a proton-rich nucleus undergoes by beta plus decay, a positron is emitted, and when he annihilates with an electron, 2 high energy gammas are emitted in almost opposite directions. These gammas are detected in a PET scanner, and coincidence occurs when they are detected simultaneously. The line connecting these two detection points is called the line of response. Spatial resolution is defined as the minimum distance at which 2 points can be distinguished in an image, and is affected by the depth of interaction. This depth defines the exact location where the gammas interact within the crystal, and this figure exemplifies how well we can estimate the line of responses with depth of interaction. So the goal of this project is to optimize a flat panel PET scanner in terms of spatial resolution and image distortions. And to achieve this, I will follow 3 objectives. So the first one, I want to study how good is the depth of interaction within the crystal at a small scale. Is composed by a LISO scintillator and 2 silicon photomultipliers at its ends. Next, I want to determine the depth of interaction and characterize your resolution. And finally, I want to achieve the goal of this project. So the surface of the sidewall of this crystal can be polished or rough. And the analysis of the roughness, the impact of this roughness on the depth of interaction was already studied by collaborators. And one of my tasks will be to extend this model and include and photon transport with wavelength resolution and enhance the efficiency of detection of these photons in the silicon photomultiplier. event will produce two signals, one in the upper and another in the lower sensor. I will study your normalized difference and obtain the position within the crystal, and this way I will parameterize the depth of interaction. Finally, I want to optimize the entire scanner over the entire field of view, which is composed by two detection heads, and this way I will study the depth of interaction on the entire scanner over the entire field of view.
So now, if anyone has a question, please raise your hand. Okay, awesome. One question over there.
You mentioned
Sorry, could you speak up a little?
Sorry.
Yeah, higher. Thank you.
You mentioned that you use encapsulated techniques, I guess.
Okay. Thank you. The crystal, the laser scintillator, will be encapsulated with an instant reflector film, and this way the light transmitted will be optimized, and we optimize as well the reflection and minimize the absorption. As we'll just have 2% of absorption between the hair layer and this film, and yeah, this way.
Thank you.
Any more questions?
Why use N3 and not Gen 4?
Okay, N3 is a front-end advanced for Gen 4 toolkit. Gen 4 is a big library, and this way it's more easy to simulate particles and actually simulate the optical photons, because yeah, you can simulate effectively, and yeah, it's more easy.
Okay, I just have here a final question. Could you go back to figure 2 and explain it maybe a little bit better?
Okay.
Yeah, this one.
The dots are the emission points. So the emission points, we presume the nucleation occurs here, and then this line, along this line, the gammas are emitted, and the arrows indicate the position where the gammas are detected. So this is for a true coincidence, but this one is for random and scatter coincidence, which can provide false floors and produce noise in the image and distortions.
Okay, thank you. Thank you, Marta. Thank you for the question.
So, our next speaker will be Gonçalo Almeida, who has been developing a system for determining the atomic composition of various materials using LIBS. So let's hear from Gonçalo's main contributions and why is this important. Thank you.
My name is Gonçalo Almeida, and today I'm going to introduce you to laser-induced breakdown spectroscopy, or simply known as LIBS. LIBS is a powerful analytical technique used to determine the elemental composition of a sample through the formation of a high-temperature plasma, induced by an intense short laser pulse. This laser pulse is focused onto the sample surface, and it is used as an energy source to cause the ablation or vaporization of atoms from the surface, which are further excited to form a short-lived and extremely hot plasma. As the plasma cools, the excited atoms decay to lower energy states, emitting photons with characteristic wavelengths. The emitted light from the plasma is dispersed into different wavelengths and detected using a spectrometer. Finally, data analysis tools are used to identify and quantify the elements based on their spectral signatures. LIBS offers several advantages over other analytical techniques, making it a valuable tool in a wide range of applications. For example, LIBS is a point-and-shoot technique, typically requiring minimal to no sample preparation. LIBS provides real-time analysis thanks to the high repetition rate of the laser, which is especially useful for on-site and in-process monitoring. It offers high sensitivity and high spatial resolution. It can analyze a broad range of materials, regardless of their phase, and can detect all the elements in the periodic table. LIBS is widely used for quality control in metallurgy and other industries. In the medical field, it is applied to the analysis of biological samples and human tissues. LIBS also finds applications in defense and security for detecting dangerous materials and chemical agents. At last, it can be used in mining exploration or even in space exploration, since LIBS technology has already been deployed on Mars. My project focuses on developing a LIBS system that incorporates an ultra-short pulsed laser with femtosecond pulse durations, operating at high repetition frequencies to conduct elemental analysis of various samples. Different configurations will be evaluated on a test bed. For example, we can vary the pulse energy, the pulse duration and the repetition rate of the laser. We can also control spectral resolution, spectral range and sensitivity of the detector. It is important to understand how each configuration affects the results in order to improve the accuracy of the analysis. I will also be responsible for designing the optical circuits for beam delivery and signal collection using the ray tracing software ZMAX. I will design and test various optical configurations for compact spectrometers to be integrated into a portable LIBS instrument. This work is part of the LIBScan project, resulting from the collaboration of multiple teams with different expertise. Sarspect, a private company from Porto, which is the promoter of the project, Inesctec from Faculdade de Engenharia da Universidade do Porto, and ISTID from Instituto Superior Técnico, where I'm included. Thank you for watching. So, hello everyone. In this presentation I will try to be more clear about what are the objectives of my project, and I will also explain the reasons why I'm going to use ultra-short pulse durations. So, as I said in the video, the main objective of my project is to build a system for determining the atomic composition of different materials using laser-induced breakdown spectroscopy. This technique consists of examining the light emitted from a plasma that is produced on the surface of the sample using a very intense laser pulse. My main contribution to the project consists of finding the optimal experimental conditions to improve LIBS performance for elemental analysis. I will explore in particular the potential of ultra-short laser pulses to provide more reliable and accurate results in comparison to the traditional approach where nanosecond lasers are used. Later in the project, I will also optimize the optical design of a spectrometer using a ray tracing software called ZMAX. So, what is the influence of the pulse duration? Using ultra-short laser pulses, we can reduce the thermal effects on the sample. This contributes to minimal sample damage, which is important for more sensitive applications. We can reduce the variability of the analysis between different pulses. We can improve spatial resolution and also increase signal-to-background ratio, which is helpful, which is useful for to resolve better the spectral lines. However, there are also some drawbacks. For example, the plasma that is generated is less dense and is shorter in lifetime, which means that it is more difficult to detect the plasma and it is more difficult to obtain high sensitivity levels. Also, it is much more complex and it is much more expensive to produce this type of pulses with these ultra-short durations, which means that this type of analysis is still not widely accessible. In order to find the optimal experimental conditions, there are different things that we can try. We can change the laser parameters, such as the pulse energy and the pulse duration, and in this way we can control the laser intensity that we use to generate the plasma. We can select the detection window, which lets us control when the signal is recorded. This is important because typically we want to avoid the continuum background, the initial continuum background from the plasma, which is very dominant. In terms of the focusing optical system, we can vary the focal plane at the sample and vary the interaction area. The interaction area depends on the diameter of the beam and on the distance between the focusing lens to the surface of the sample. And finally, for the collection optical system, we can vary the collection angle. Something that will be part of my study is to understand if the plasma emission is isotropic or not. And we can also vary the acceptance angle of the plasma light. If we need more sensitivity, we can increase the acceptance angle. However, we must also be aware that we may lose resolution. So as we can see, there are different things that can influence the signal from the plasma that we collect. And in my investigation, I will try to approach each one of them. Thank you for listening.
Does anyone have questions?
I have a question. First of all, great presentation. I'm just wondering, what's like the typical energy to ignite the plasma on the surface?
So for femtosecond pulsations, we typically need more than 10 to the power of 13 watts per centimeter square. However, this highly depends on the sample properties and optical properties and thermal conductivity, so there is not a super defined value for it. It also corresponds to some microjoules for the laser pulse energy.
Yeah. Okay. Anyone else? No? So I have a question for you, Gonçalo. I was wondering what will be your main contributions to optimize the design of this spectrum?
So that part of the optimization will only occur at the later part of my project. I will try to improve somehow the resolution and sensitivity. For example, I can choose a more complex optical design. I can choose different mirrors and diffraction gratings to minimize the optical aberrations that may occur. I can try to minimize the stray light. Stray light is an unwanted light that may be reflected from the spectrometer and can influence the analysis, and many other things.
Okay.
I will try.
So thank you, Gonçalo. So our next speaker will be João, that has been working on the development of wearable sensors for real-time stress monitoring in firefighters. So I think we are all curious about to hear his contributions. So let's give us to João a round of applause and let's hear from him.
Hello, I'm João Oliveira, a physics engineering student. My master thesis is about wearable sensors to evaluate stress and enhance assisted rescue response, supervised by Dr. Helena Alves. Stress is a natural physiological and psychological response to challenges, but when it becomes chronic, it can lead to serious health problems, such as cardiovascular diseases, mental health disorders, and weakened immune systems. Due to the high risk and unpredictable nature of their work, firefighters are especially vulnerable to high levels of stress. Their exposure to extreme physical demands, life-threatening situations, and hazardous environments places them at greater risk of issues like anxiety, depression, and burnout. 45% of on-duty firefighter deaths are attributed to cardiovascular events, and in 2024, a 60-year-old Portuguese firefighter died while on lunch break between helping to fight a fire in Oliveira de Asmeios, here in Portugal. This highlights the critical need to monitor and manage stress effectively to ensure their well-being and operational safety. Wearable sensors offer a promising solution to this problem, as they have proven to be essential tools in healthcare, sports, and occupational safety. Chest-mounted devices ensure stable contact with the skin and capture accurate electrocardiogram data, even during intense physical activity. In this project, called SafeFire, 3 prototype designs have been tested: the sweatshirt, the singlet, and the vest. Although the sweatshirt and the singlet both offer great mobility, they fail to ensure adequate tightness on the electrode on the chest, which affects the signal quality. So, the vest stood out as the most reliable one, as it resolves issues with both fit and comfort. There are also 2 electrode materials still being tested: the metal-plated polyamide fabric and the metal-doped polyurethane foam. As for the sensors, MoveSense is the main sensor chosen for field use, as it is compact and programmable. However, the scientist is also being tested to see if it is a viable option. Data collected from the prototypes include electrocardiogram signals, movement metrics, and other physiological parameters. The analysis of the PQRST structures present in electrocardiogram signals has been identified as a reliable metric to address stress identification, and that's why that metric signal is the mainly focused one for now. So, a Python-based code was developed to analyze ECG signals by identifying these wave structures and calculating their amplitudes and relevant time intervals. This code analyzes each minute and classifies it as acceptable or unacceptable, taking into account the mean values resulting from that whole minute and some ranges of values previously labeled as standard. Any values that are not in these ranges are excluded and will decrease the acceptance percentage. Minimum thresholds were also implemented to filter out noise and to better detect when the device was not being used, because up until now, when running the code, there was still the need to visualize the actual signal to ensure that the results agreed with its behavior. Now, the current focus is on refining the code to improve accuracy and to ensure it can handle real-time applications. Some possible future implementations will include heart rate variability and a Fourier transform to better clear the signal of unwanted noise. That's it, I hope you liked it and thank you for watching. Só uma coisa? Tá. Hi, so I'm here to give a little more aspects of this project. Okay. Field test involved 15 firefighters with plans to expand to 40 more. They used the devices on daily operations and control simulations with the help of daily surveys to assess fatigue and effort levels. These daily operations could include cutting down trees, being part of a rescue ambulance crew, among other activities. Some controlled simulations were done in LAFE, the Forest Fire Studies Laboratory, where the firefighters simulated real forest fire activities, like hose dragging and burning branches to simulate forest fire to see how they would react, how their body would react. Some static exercises were done before and after these activities to see those effects. Okay. There were a lot of preliminary difficulties as the best signals presented some acceptance percentages between 60 and 95%, but there were some signals from one firefighter that presented only around 30%. So we actually came to the hypothesis that his device was too loose, and it was actually confirmed by our supervisor. So he would need to change devices to a tighter one, because the electrode tightness is very important. Some signals also presented very low amplitudes, and after consulting a medical doctor, we came to the conclusion that the most important things, the most important aspect to analyze is actually the shape of the PQRST structures. So the time intervals had more attention than the actual amplitudes of the signal. The signals that came from the field tests were not that satisfactory as they presented a lot of irregularities for proper analysis, most of them being from high effort activities. So the preliminary results were not that conclusive, as only the signals from one firefighter was good for analysis. In the future, we'll try to continue the prototype development, the field testing, and the data processing. And once they're finished, we'll try to implement the real-time monitoring system. To do so, we'll acquire a lot more data with different system configurations. Thank you for your attention. If you have any doubts, you can now.
So, okay, go. So, do you have any plans on commercializing?
That's not my department, sorry. For now, we're just testing it and actually improving it, so
Yeah,
ask me.
An ambition or something like that?
For now, we're only asking, we're only trying to point to firefighters, so, but yeah, maybe one day we'll try to.
Yeah, that would be really nice.
Yeah.
That's what I'm asking.
Yeah.
Just one question. We had the presentation from Inês earlier today.
Yeah.
How does your work interact with theirs?
Okay, that's a good question. We have, as I said, 15 firefighters, 15 volunteers. We had different data. So these were my problems that I found. I know Inês found different problems. For example, I know I didn't refer, of course, because it was not my. We stayed in contact, but one of our firefighters actually had a heart problem. They detected it. So her data was not that good for analysis, as it was different from the others, the normal firefighters that didn't have that disease, not disease, but that problem. So yeah, but when we came to conclusion to anything, we're all trying to improve the same code, so it all comes down to the same purpose. Yes. Yeah.
Hi, thank you for the presentation. Now, I might be overthinking it, but I think that what you are doing, like firefighters doing like mock tests of like them dragging
the hose.
Yeah, the hose, or taking down fire on burning branches, and using it to assess like the stress levels of how. Do you then like extrapolate to like an actual firefighting situation? Because since this is a test, obviously the stress levels would be much lower. Or is that not a problem?
I'm sorry, I don't know if
for example, you are using like mock simulations, right?
Yeah.
Not real firefighting
Oh, okay.
situations, which are inherently less stressful.
Of course, it is.
So, do you then extrapolate it, or is that not a problem?
Yeah, we'll try to extrapolate it, and there is a big test being planned already. I don't know when, I think it's March that is going to happen, where they'll actually start burning, not to the point that it is not controlled, but it's also always controlled, but still to try to cause a little more stress. But since I started in the winter, there are not that many forest fires right now, so we can't really test it. And we don't want to cause any forest fire just to test it out. That's one constraint.
Anyone else? So I just have one curiosity in keeping up with the question from Gonçalo about the ambition. So how far are you from achieving a real-time device for this type of?
Right now it's still a little far, because the system is not that, the code is not that independent. As I said, we needed thresholds to trying to figure out when the device is not being used and when it is being used. So we're still at this point where we tried to tell them when it is being used, and now we're trying to also improve the analysis of the code to have reliable results.
Okay. Good luck.
Thank
Round of applause to Okay, we are almost ending today's session. Now the next speaker and the last speaker of today's is probably the better beer plus hair combo of the class. He's going to talk about thermal channel implementation at Fissionist. Please welcome our nuclear engineering Jesus, Antonio Lourenço.
Hello, my name is Antonio Lourenço, and I'm here to talk about my dissertation project, Thermal Channel Implementation at Fissionist. Nuclear energy has been a vital part of the global energy mix since the 1960s. Unlike other energy sources, nuclear fission provides a stable, weather-independent supply of electricity while maintaining one of the lowest carbon footprints among large-scale energy solutions. But with 1/3 of the nuclear workforce nearing retirement by 2033, the need for well-trained professionals has never been greater. Fissionist is a nuclear reactor simulator developed at Instituto Superior Técnico, which will help training the next generation of nuclear engineers and reactor operators. What sets Fissionist apart is its use of real components, including the control rods. The simulator is designed to recreate neutron dynamics and power fluctuations across a range from less than 1 milliwatt to over 1 megawatt. The simulator is designed to replicate the operational conditions of Portugal's only research reactor, the Reator Português de Investigação, or RPI. The RPI was built from 1959 to 1961 and operated for 55 years until it was shut down in 2016. It was located in Bobadella and is currently part of the Campus Tecnológico e Nuclear. While originally intended for training personnel, it was also used for research and to produce medical isotopes. Nuclear reactors rely on a process called nuclear fission, where the nucleus of a heavy atom gets struck by a neutron and splits into smaller nuclei. This splitting releases a large amount of energy, mostly as heat, along with more neutrons that continue the chain reaction in a controlled process. While the chain reaction and control mechanisms have already been implemented by other students, there is one key component missing: temperature. Temperature plays an important role on the behavior of the reactor. As fuel heats up, the reactivity is affected through a property known as the temperature coefficient of reactivity. Reactors are designed to have a negative temperature coefficient, meaning an increase in fuel temperature reduces reactivity. This ensures that as the fuel heats up, the reaction slows down, stabilizing the system. Additionally, temperature must be extracted from the reactor core, which is done through cooling circuits. In the case of RPI, there were two isolated circuits. The primary circuit carried water directly through the reactor core, where it absorbed heat, and then to a heat exchanger. Here, the heat was transferred to the secondary circuit, which carried the heat to a cooling tower, where it was dissipated. The objective of my master's thesis will be to simulate the response of flow, pressure, and temperature detectors which existed at RPI. This will require reading the control commands for the cooling circuit's pumps, as well as the power output from the neutron channels using an analog to digital converter, simulating the water flow rates and temperature at critical points in the system, and outputting the simulated detector signals through digital to analog converters so that they can be interpreted by limit controllers and the fissionist security channels. Lastly, the temperature dependence in the kinetic equations will also be implemented. Thank you for watching. Thank you for watching. I hope you liked it. Now I'm going to elaborate on some topics I covered on the video. So first, why is nuclear fission energy important? In the evolving landscape, our countries are trying to meet zero carbon, carbon zero balance in their energy sources, as well as countries that are trying to diversify their energy sources in order to rely less on trading with certain countries. Diversifying energy is important. In the case of nuclear, it can fulfill an important role, which is to have a baseline for the entire system. This means that countries that rely on nuclear use it to output a constant supply of energy and then use other energy sources to meet the current demand. It is used for that because nuclear is one of the energy sources that can be the closest to its maximum efficient for the most amount of time, according to the US Department of Energy. It is also among the safest and cleanest energies in terms of greenhouse emissions, according to our modeling data. Its main cons are the fact that it costs so much to build, not just to build the reactors and to build the equipment, but also to get the specialized workforce that nuclear requires. For that, Fissionistic is a simulating research reactor that can train such operators. It is different from other reactors from normal research reactors in the way that it is safer because you can train emergency scenarios without actually being in an emergency scenario. And it is different from other simulators because it is more immersive, as it has actual real components from the reactor. When I entered Fissionist to start working on this, I was jokingly told that the people who had been working with this before had to build a reactor without neutrons, and now my job is going to be to build a reactor without water. In order to do that, there will be a new cooling circuits module. This is a diagram of the new module that shows more or less how the components interact. The Raspberry Pi is going to be the microcontroller that receives information from the pump state and the reactor power, and it then outputs the simulation of the detectors that exist at FAE through the digital channel converters to two limit controllers that will alert the rest of the simulation if something is going wrong, such as the primary circuit flow being too slow. There will also be the simulation of the 6 temperature recorders. Additionally, the temperature will also be included in the simulation for the reactor power that has been done previously by our students. Thank you. If you have any questions.
We have already a pre-registered question over there, so go ahead, Gonzalo.
Yeah, nice presentation, really nice. Just one question. Another cons that I can see is that reactors may take a while to be constructed. But that's not my question in here. Is that the Chinese are actually you're using a uranium-based reactor, right?
FPE was used to uranium enriched at 19.75%.
Yeah, okay. But for instance, Chinese are also investing in thorium-based. So
yes.
What's your take on that? Can these results be?
Right now, there are many technologies that have existed for decades, but are now being developed, such as thorium reactors, and the Chinese are also investing in, for example, small modular reactors. The small modular reactors would actually help with the construction time constraints of reactors, since they can, in theory, be built outside the place where the reactor builder will be, building will be, which means that you can build a building and import a reactor to put in a mill, and you don't have to wait for the time it takes to build the full reactor.
Actually, I was just wondering if you're taking, what do you think of the two options? What's your take on that?
On what option, sorry?
If this can also be used in thorium-based.
Fissionist will help train operators. If I'm not entirely sure, but if the thorium reactors have a similar control mechanism, if people that are trained with this reactor can also.
Wonderful, then. Thank you.
Okay. Any other question? I have here one question for you, which is, you talk about all this takes into account the temperature, right? Is there any other factors that you're missing out of your project?
Most of the things that have not to do with temperature have already been done, but there are some things that still need to be done. For example, the control rods that exist there right now are placed as it was shown in a video. They're in a horizontal. They're basically on a table. In a reactor, they would be vertical, which means that there might be like some slight differences, and as such, those control rods will have to be put in a vertical position. There already is a table made for that, and that would require recalibrating all the things that have to do with the control rods, which I will also participate in.
Okay, perfect. If there's any other question, we're gonna end this session, I guess. Thank you, Antonio. So we're gonna sign up tomorrow. I think it's the same hour. It's the same today's hour, yeah.
So thank you. So basically, just before everybody leaves, tomorrow there is no opening session, so we'll all be back here at 9:30 a.m. tomorrow.
Yeah, let's have another great day of presentations tomorrow, guys.
Yeah, see you all.